The rain taps against the window of the small observatory control room, each drop catching the glow of monitor screens before sliding into darkness. Sarah watches the telemetry scroll past, numbers that represent a spacecraft sitting in nothing, balanced on the edge of falling forever. She's been awake for 36 hours straight, shepherding the telescope through its final approach to a point in space that doesn't really exist. Not as a place you could touch or see, just a sweet spot where the mathematics of motion allows a machine to hover without effort, almost. The coffee has gone cold again. Outside, the storm moves across the desert in grey sheets, obscuring the mountains. Inside, the room hums with the steady breath of computers translating signals that left the spacecraft 28 seconds ago, travelling at the speed of light across 1,000,000 miles of emptiness. 28 seconds is an eternity when you're trying to thread a needle with a robot the size of a bus. Approaching orbital insertion corridor, calls Marcus from the navigation console. His voice carries the careful neutrality of someone who's done this dance before, who knows that excitement leads to mistakes. Sarah nods, her fingers hovering over the command sequence that will fire the thrusters for exactly 17 seconds, nudging their telescope onto a loop around an invisible point that exists only in the language of gravity and spin. The Lagrange points aren't parking lots in any ordinary sense. They're more like those moments in a spinning top's wobble, where it seems to hang suspended, neither rising nor falling, caught in a negotiation between forces that should tear it apart. Between any two bodies locked in gravity's embrace, the Sun and Earth, Earth and Moon, a planet and its satellite, there exist 5 such moments frozen in space, 5 places where a smaller object can keep pace with the larger body's dance without constantly burning fuel to stay in position. Sarah thinks of them as harbours, though that's probably too solid a word for what they really are. Harbours suggest docks and moorings, something you can tie yourself to. These are more like the eye of a hurricane, calm centres in a rotating storm of gravitational forces. You can rest there, but never truly relax. The universe is always trying to push you out, gently but insistently, and you have to keep correcting, keep adjusting. Tiny burns of hydrazine or pulses of ion thrust, whispers of force that add up to staying put. The one they're heading for sits 1,000,000 miles from Earth, directly opposite the Sun. From that vantage, the Earth, Moon, and Sun all cluster together in one direction, leaving the rest of the sky dark and cold and perfect, for looking outward into the deep night where galaxies sprawl like spilled salt across black cloth. This is L2, the second Lagrange point of the Sun-Earth system, and it's where humanity parks its most ambitious eyes. She remembers learning about orbits as a child, the simple picture of objects falling around Earth in neat circles. Later came the complication. Orbits are always falling, but falling sideways fast enough that the ground keeps curving away beneath you. You're perpetually missing the planet, threading the needle between escape and impact. But in a frame of reference that rotates with 2 bodies, say, a coordinate system that spins with the Earth as it circles the Sun, something strange happens. The centrifugal effects that emerge from that rotation add to the gravitational pulls in ways that create these 5 special regions where everything balances just so. Not balanced like a ball on flat ground, stable and happy. More like a marble balanced on top of a beach ball, possible in theory, requiring constant attention in practice. Well, 3 of them anyway. L1, L2 and L3 are unstable saddle points, ridges you can perch on if you're careful. L4 and L5, the points that form equilateral triangles with the 2 bodies, are different. They're shallow bowls where objects can settle into lazy orbits, following tadpole or horseshoe paths that loop around the point without drifting away. Jupiter has thousands of asteroids lounging in its L4 and L5 points, fossil remnants from the solar system's formation, trapped in those gentle gravitational valleys. Burn sequence armed, Sarah says, and her voice sounds far away even to herself. This is the culmination of 8 years of design, 3 years of construction, 2 years of testing, and 6 months of travel. The telescope cost more than a small nation's GDP, carries instruments that can see wavelengths of light the human eye never evolved to detect, and right now depends entirely on 17 seconds of controlled fire. Marcus counts down. Mark in 10, 9, 8. The spacecraft doesn't actually sit on the point itself. That would be like trying to balance a pencil on its tip. Theoretically possible, practically absurd. Instead, it traces what they call a halo orbit, a three-dimensional loop that circles the invisible point like a moth around a flame, except the flame isn't there and the moth is solar-powered and following equations that would have made Newton weep with joy. These orbits rise above and dip below the plane of Earth's orbit around the Sun, keeping the spacecraft in constant sunlight for its solar panels, while maintaining a clear view of both Earth for communications and deep space for science. 3, 2, 1, burn. The telemetry stutters, updates. The velocity vector shifts infinitesimally on her screen, rotating the spacecraft's trajectory from an approach hyperbola into the first graceful arc of its permanent waltz. Sarah holds her breath without meaning to, watches the numbers settle into their predicted ranges, green lights cascading down the status board like a slow waterfall of confirmation. Capture confirmed, Marcus announces, and the tension breaks like glass. Someone cheers in the back of the room. Sarah allows herself a smile, small and private, the kind you wear when you've just parked a billion-dollar machine in a spot that exists only as a solution to differential equations. The point they've reached has a strange property. From here, the Sun is always in the same direction, and so is Earth. The spacecraft's sun shield, a tennis court-sized structure of layered captain and aluminum, unfolded 2 weeks ago in a process that took 6 hours and aged Sarah 5 years, can block all 3 sources of heat at once. Behind that shield, in permanent shadow, the telescope's instruments will cool to just a few degrees above absolute zero, cold enough that their own heat won't swamp the faint infrared whispers from galaxies born when the universe was young. At Sun-Earth L1, a different class of spacecraft keeps watch. That point sits between Earth and Sun, upstream in the solar wind, and the machines there stare at the Sun's roiling surface, watching for eruptions that could damage satellites or power grids. They're sentinels, giving Earth anywhere from 15 minutes to an hour of warning when a coronal mass ejection comes howling outward at 1,000,000 miles per hour. From L1, you see the Sun's face clearly and constantly. No eclipses, no interruptions, just endless vigil. L3 sits opposite Earth on the far side of the Sun, and it's the least useful of the group. Too dynamically unstable, too expensive to reach, too difficult to communicate with when the Sun sits between you and your spacecraft for weeks at a time. Science fiction writers sometimes park secret planets there, hidden Earths riding our own orbit but forever out of sight behind the Sun's bulk. In reality, perturbations from other planets would reveal such a world quickly, and we've looked anyway, just to be sure. There's nothing there but empty space and unused potential. The Earth-Moon system has its own Lagrange points, closer to home and more immediately useful. EML1, sitting between Earth and Moon, serves as a conceptual gateway for missions heading to or from the lunar surface. EML2, beyond the Moon's far side, offers something more interesting. A place where a communications relay can hover, maintaining constant line of sight with both Earth and the Moon's hidden face, that hemisphere that always turns away from us, perpetually shy. Sarah watches the telescope begin its first science observations, cameras and spectrometers waking from cruise mode like a sleeper stretching after a long journey. The targets are prosaic at first, calibration stars, objects whose properties are well known, used to verify that the optics survived the voyage, and the cryocoolers are working as designed. Later will come the real work, staring at patches of apparently empty sky for days at a time, collecting photons that left their sources when the universe was a fraction of its current age, light that's been travelling for most of cosmic history to reach this particular arrangement of mirrors and detectors. Station keeping will become routine, she knows. Every few weeks the flight dynamics team will calculate a small correction burn, a few meters per second of delta V to nudge the spacecraft back onto its nominal path. Solar radiation pressure, literal photons pushing on the sunshield, will perturb the orbit. The Moon's gravity will tug irregularly. The model they use assumes 2 bodies, Sun and Earth, but reality includes Jupiter and Venus and Mars, all pulling in their own subtle ways, and the Earth itself isn't perfectly spherical, and the Sun's radiation pressure varies with the solar cycle. The universe is messier than the mathematics that describe it, and engineering is the art of succeeding despite that messiness. The halo orbit the telescope traces isn't circular. It's more of a lopsided oval in 3 dimensions, carefully chosen so that the spacecraft never passes through Earth's shadow. No eclipses means no thermal cycling, no batteries depleting and recharging, no stress on components designed to operate at constant cryogenic temperatures. The path keeps the sunshield properly oriented, always edge onto the sun, always blocking the view of Earth and Moon, maintaining that precious darkness behind which the telescope peers into deep time. Other spacecraft have called L2 home before this one. Early missions mapped the cosmic microwave background from here, measuring the afterglow of the Big Bang with exquisite precision, finding patterns in that ancient light that revealed the universe's composition and fate. Their data rewrote cosmology, turned speculation into measurement, answered questions humans had been asking since we first looked up, and wondered what all those lights meant. Sarah remembers studying those missions in graduate school, learning how they stabilized their orbits, how they calibrated their instruments, how they dealt with the slow accumulation of energetic particles that space hurls at anything that ventures beyond Earth's magnetic shield. L2 sits outside that protection, exposed to the solar wind and cosmic rays, and every spacecraft that goes there must armour itself accordingly, shielding its electronics and accepting that eventually radiation damage will end the mission. The advantages outweigh the risks. At L2, the thermal environment is predictable. Stable temperatures make for stable measurements, and stable measurements make for good science. The lighting is constant, which simplifies power management. Communications with Earth are straightforward. No occultations, no periods of enforced silence, and most importantly, the view is unobstructed. No warm Earth glowing in infrared, drowning out the faint signals from distant galaxies. Just cold darkness and patient observation. The engineering required to make it all work fascinates her in ways she doesn't fully understand herself. The sunshield unfolds like origami in reverse, layer after carefully designed layer, each one blocking a portion of the sun's heat, so that the final layer, closest to the telescope, reaches temperatures cold enough to freeze air solid. Attitude control keeps everything aligned, reaction wheels spinning to maintain orientation, momentum dumped occasionally by firing thrusters, a constant juggling act of angular momentum and propellant budgets. At L1, the engineering priorities differ. Spacecraft there face the sun directly, deliberately, instruments drinking in the light and radiation to monitor solar activity. They need different shields, different orientations, different orbits chosen to keep communications with Earth open, while staring into that nuclear furnace 93 million miles away. But the basic principle remains the same. Find the sweet spot, trace a loop around it, and nudge yourself back on course when you drift. The science that flows from these harbours transforms astronomy. Space weather predictions improve with better solar monitoring from L1. Exoplanet hunters use infrared telescopes at L2 to watch stars for the tiny dips in brightness when worlds transit their faces. Studies of star formation peer into dust clouds that visible light can't penetrate, seeing protostars ignite in their cocoons, and cosmologists map the structure of the universe itself, galaxy by galaxy, building three-dimensional charts of matter's distribution across billions of light years. Marcus brings her another coffee, this one actually hot. "First light looks good," he says, and she nods, scrolling through spectra that mean nothing to her, but everything to the astronomers who will spend years analysing them. The data begins its journey earthward, packets of ones and zeros riding radio waves across the Gulf, arriving 28 seconds after they're sent, accumulating in storage arrays where scientists will sift through them like prospectors panning for gold. She thinks about the misconceptions, the questions journalists always ask when trying to explain these missions to the public. No, there's no gravity-free zone. Gravity is everywhere. It's the whole reason the Lagrange points exist. No, the spacecraft doesn't anchor to anything physical. There's no there, just a location where forces balance. And no, maintaining position doesn't require huge amounts of fuel, just tiny corrections, teaspoons of thrust spread over months and years, enough to counteract the slow drift that perturbations impose. The restricted three-body problem that yields these points is an approximation, she knows. Reality includes every massive object in the solar system, all pulling and pushing in their own ways. The sun isn't perfectly spherical. The Earth and Moon don't orbit in a perfect plane. Solar radiation pressure varies, but the Lagrange framework remains useful because it captures the essential dynamics, provides a map that's accurate enough for navigation even if it's not perfectly true. All models are wrong. Some are useful. Looking ahead, she imagines future missions, fuel depots at EML1, staging points for lunar sorties and Mars missions, fleets of telescopes at L2, working in concert to achieve baselines impossible for any single instrument, communications relays at Earth-Moon L4 and L5, providing constant coverage of cislunar space. Sample return missions using the Earth-Moon Lagrange points as waypoints, dropping off precious cargo before diving back toward the moon or beyond. Autonomous platforms that ride the weak stability boundaries, those gravitational manifolds that connect different Lagrange points, allowing nearly propellantless transfers if you're patient and clever about timing. Other worlds have their own Lagrange points, 5 accompanying every two-body partnership. Mars and the Sun, Jupiter and the Sun, where Trojan asteroids swarm by the thousand, even small asteroid moons create miniature versions of these same patterns. Wherever two objects dance in mutual orbit, the 5 notches appear, inevitable consequences of gravity and rotation. The rain has stopped, she realizes. Dawn lightens the eastern sky, and the desert emerges from shadow, brown and grey and beautiful in its austerity. Sarah stretches, joints popping, exhaustion finally catching up now that the critical phase is over. The telescope will orbit its invisible point for years, maybe a decade if the cryocoolers and electronics hold out, staring into darkness and finding light. She leaves Marcus to monitor the routine observations and steps outside, breathing air that smells of wet creosote and ozone. 1,000,000 miles away, a machine she helped design traces its loop around a point that exists only in mathematics, a harbour made of timing and geometry and tiny patient burns. It's not falling, and it's not floating. It's balanced in motion, perpetually catching up to 2 worlds that themselves never stop moving. Above her, invisible in the brightening sky, Earth continues its ancient orbit, and at 5 specific places in that orbit's geometry, spaces exist where humans have learned to park their ambitions, their curiosity, their hunger to see what the universe looks like from somewhere other than the bottom of a gravity well. The Lagrange points aren't destinations exactly. They're vantages, perches, quiet corners in a cosmos that never stops wheeling. Sarah thinks about all the light streaming toward that telescope right now, photons that began their journey before Earth existed, before the sun ignited, before anything but hydrogen and helium and darkness filled the universe. That light will arrive at precisely calibrated mirrors, bounce through precisely figured optics, strike precisely cooled detectors, and become data. Become knowledge. Become answers to questions nobody knew how to ask when she was young. The sun clears the horizon, and she raises a hand to shade her eyes. Somewhere out there, invisible and unreachable but precisely located, a point in space waits, and a spacecraft circles it like a faithful moon around a planet that isn't. There. It will stay for years, nudged and corrected, shepherded by engineers and guided by physics, until its fuel runs low, or its instruments fail, or its mission ends because there's nothing left to discover. But that day is far away. For now, the telescope stares into the deep black, and the data flows earthward, and Sarah stands in the desert dawn, tired and satisfied, thinking about harbours that have no docks and parking spots, that exist only in the language of motion and force. The universe keeps turning, and we've learned to find the still points in that turning, the places where we can rest, not forever, but long enough to see what needs seeing, to measure what needs measuring, to understand just a little more about this strange and beautiful cosmos we inhabit. She walks the perimeter of the facility, letting her mind drift the way it does when exhaustion becomes something close to meditation. The gravel crunches under her boots, and she notices details she normally wouldn't. The way the morning light catches on quartz fragments, the tracks of some nocturnal creature that crossed the path while she was inside watching numbers, the distant call of a hawk beginning its hunt. It occurs to her that she's been so focused on the far that she's forgotten the near, that the same physics that governs spacecraft also governs hawks and stones, and the way morning spreads across a desert. Inside, the team will be settling into the rhythm of operations, the long slow dance of maintaining a mission that measures its objectives in years rather than days. There will be anomalies to investigate, software patches to upload, science proposals to evaluate, budget meetings and status reports and all the mundane machinery that keeps a spacecraft functioning across 1,000,000 miles of nothing. But right now, in this particular moment between the crisis of insertion and the routine of operations, there's a pause, a breath, a space where she can think about what they've actually accomplished. The transfer from Earth to L2 took 6 months, but it wasn't a straight line. Nothing in orbital mechanics ever is. The spacecraft followed what the navigators call a trajectory arc, spiralling outward from Earth's gravitational influence, while the sun's pull gradually took over as the dominant force. They fired the engines in carefully timed bursts, each burn calculated months in advance but adjusted in real time based on tracking data, nudging the path until it intersected with the halo orbit at just the right angle and velocity. Too fast and the spacecraft would overshoot, sailing past the point into the solar system's depths. Too slow, and it would fall back toward Earth, wasting fuel and time in a second attempt. Sarah had dreamed about those burns, literally dreamed about them in the weeks leading up to each maneuver. In her dreams, the numbers were always wrong, the velocity vectors pointing in impossible directions, the spacecraft tumbling uncontrolled while she watched helplessly from her console. She knows enough about psychology to recognize anxiety expressing itself in the language of her profession, but knowing doesn't make the dreams any less vivid or the relief of success any less sweet. The concept of weak stability boundaries fascinates her more than it probably should. These are regions of space where the gravitational influences of multiple bodies create channels, invisible highways that a spacecraft can follow with minimal propellant expenditure. They're related to the Lagrange points, but more extensive, forming networks that connect different parts of the solar system in ways that aren't obvious from simple two-body orbital mechanics. Some missions have used these pathways to reach the moon or asteroids, trading time for fuel, taking months or years to coast along these gravitational rivers, rather than burning directly to their destinations. She imagines a future where spacecraft routinely use these manifolds, hopping from one Lagrange point to another like stones across a stream, building up speed or changing direction by carefully timing their passages through each point's sphere of influence. It would require patience and precision, but both are cheaper than propellant when you're trying to move large masses across interplanetary distances. Fuel depots at the Lagrange points could serve these travellers, autonomous stations dispensing hydrazine or xenon to spacecraft that need a top-up before continuing their journeys. The Earth-Moon L4 and L5 points remain largely unused despite their stability. They sit 60 degrees ahead of and behind the Moon in its orbit around Earth, forming equilateral triangles with the Earth and Moon at the other two corners. Unlike L1, L2 and L3, which require constant correction to maintain, L4 and L5 are gravitationally stable, at least stable enough that small objects can linger there for thousands or millions of years without much perturbation. Earth has at least one confirmed Trojan asteroid at L4, a small rock designated 2010 TK7 that traces a complex path around the point, neither approaching nor receding, caught in the gravity well like a marble rolling around the rim of a bowl. Some proposals suggest placing communication satellites at Earth-Moon L4 and L5, creating a permanent infrastructure for cislunar operations. From those vantage points, you could see both Earth and Moon simultaneously, providing continuous coverage of the lunar surface, including the poles, where permanent shadow holds deposits of water ice that future missions might harvest for propellant and life support. The geometry is elegant. 5 points, 3 of them unstable ridges, 2 of them stable valleys, all of them useful in different ways, all of them consequences of the same fundamental physics. Sarah wonders what Lagrange himself would think of the uses we've found for his mathematical curiosities. Joseph Louis Lagrange worked out the 5-point solution in 1772 while studying the three-body problem, how 3 mutually attracting masses move under their own gravitation. It was pure mathematics to him, an interesting puzzle in celestial mechanics with no obvious practical application. He couldn't have imagined spacecraft, or that humans would someday need parking spots in space, or that his equations would guide machines carrying instruments that could detect light from the universe's childhood. That's the way of mathematics, she supposes. You discover patterns and relationships because they're interesting, because they satisfy some aesthetic sense of order and beauty, and only later, sometimes centuries later, does someone find a use for them. Number theory was recreational mathematics for thousands of years before modern cryptography made it the foundation of digital security. Calculus was Newton and Leibniz playing with infinitesimals before it became the language of physics and engineering. And Lagrange's 5 points were curiosities before they became addresses. Marcus appears in the doorway, squinting against the brightening sky. "You should get some sleep," he says, and it's not a suggestion so much as an observation of obvious fact. Sarah nods but doesn't move immediately. She's reluctant to leave, even though the critical phase is over, and there's nothing she can do now that the automated systems can't handle better. There's a possessiveness that comes with working on a mission for years, a feeling that the spacecraft is somehow hers, that she needs to watch over it personally. It's irrational, but she's learned that most feelings about space missions are. "How's the thermal balance?" she asks, because she can't quite let go yet. Marcus smiles, recognising the delay tactic. Within nominal range, the sunshield is performing exactly as modelled. Cold side holding at 47 Kelvin, warm side at 300. The cryocoolers are cycling normally. Everything's fine, Sarah. The spacecraft doesn't need you staring at it to keep working. She knows he's right, but the knowledge doesn't make leaving any easier. This is the paradox of automation. The better the systems work, the less necessary humans become, but that doesn't stop humans from feeling responsible. They've designed autonomy into every aspect of the mission. Fault protection routines that can diagnose and respond to problems without waiting for commands from Earth. Science scheduling algorithms that optimize observations based on current conditions. Even the station-keeping burns can be triggered automatically if the orbit determination software detects excessive drift. The spacecraft could, in theory, operate for months without human intervention. But theory and practice are different countries, and humans excel at handling the unexpected. The edge cases that no algorithm anticipated. So there's always someone watching, always someone ready to intervene if the automation makes a choice that seems wrong or dangerous. It's a strange partnership, humans and machines collaborating across 1,000,000 miles of vacuum, each doing what they do best, trusting each other to handle their respective domains of expertise. Sarah finally allows Marcus to guide her back inside through the control room where the night shift is handing over to the day shift, through hallways that smell of coffee and electronics, and the particular staleness that comes from buildings where the windows never open, to the small apartment the facility provides for operations personnel during critical phases. She falls asleep within minutes of lying down, her dreams mercifully empty of tumbling spacecraft and incorrect velocity vectors. When she wakes, it's mid-afternoon, and the light through the window is harsh and bright. She checks her phone before doing anything else, looking for alerts, anomalies, anything that might require her attention. There's nothing urgent, just the routine status updates that accumulate when a spacecraft is operating normally. The telescope has completed its calibration sequence and moved on to early science observations. Some distant galaxy cluster is having its portrait taken, light from 1,000,000,000 years ago focused onto detectors that translate photons into electron counts, into digital values, into scientific understanding. She showers and dresses and makes her way back to the control room, moving through the facility with the easy familiarity of someone who's spent years in these corridors. The control room is quieter now, the urgency of insertion replaced by the steady concentration of normal operations. Fewer people at the consoles, less chatter, everyone focused on their particular subsystem or instrument. This is what most of a mission looks like. Long stretches of routine punctuated by occasional moments of interest or concern. The flight dynamics team is huddled around a monitor discussing something in low voices. Sarah drifts over, curious. They're looking at the orbit determination solution, the mathematical reconstruction of where the spacecraft actually is, based on tracking data from Earth's network of radio dishes. "We're about 15 kilometers off the nominal path," one of them explains when he notices Sarah watching. "Well, within tolerance. But we're planning a small correction burn for next week to tighten things up. 3 meters per second should do it." 15 kilometers sounds like a lot until you remember that the halo orbit itself is hundreds of thousands of kilometers in diameter. At this scale, 15 kilometers is like parking slightly crooked in a space large enough to hold a city. Still, precision matters in spacecraft operations, and letting small errors grow into large ones is how missions fail. Better to correct early and often, maintaining tight control even when the margins are comfortable. The burn planning process is intricate, a choreography of orbital mechanics and propellant budgets and thermal constraints. You can't just fire the thrusters. Whenever you want, the spacecraft has to be in the right orientation, the sun angles have to be acceptable, the communications link to Earth needs to be open so you can monitor the burn in real time, and you have to make sure the exhaust plume from the thrusters won't contaminate the telescope's optics or the sunshield's surfaces. Each burn requires days of preparation, checking and rechecking the calculations, simulating the maneuver in software, briefing the entire operations team on what will happen and what to do if it doesn't. Sarah finds it beautiful in its complexity, the way everything connects to everything else, how you can't change one parameter without affecting dozens of others. is like a vast multi-dimensional puzzle where the pieces are constantly shifting, and the goal is to maintain a configuration that allows the telescope to do its science, while keeping all the subsystems healthy and the spacecraft safely parked in its invisible harbour. The engineers who designed the mission spent years thinking through these interactions, building margin into every system, anticipating failure modes and providing backup options, trying to imagine every possible problem and its solution. And yet, despite all that preparation, surprises still occur. They always do. Space is an unforgiving environment full of phenomena that don't appear in textbooks. Micrometeoroid impacts that create unexpected vibrations, solar storms that interfere with communications, cosmic rays that flip bits in computer memory, thermal gradients that cause structures to flex in ways the models didn't quite predict. Most of these anomalies are minor, solved with a software patch or an adjustment to operations procedures, but occasionally something more serious happens, and that's when the real expertise of the operations team shows itself. The ability to diagnose problems across 1 million miles of distance with limited telemetry, and even more limited ability to interact with the spacecraft. Sarah has seen missions fail, has watched helplessly as spacecraft died from causes that were obvious only in retrospect. A stuck valve, a short circuit, a software bug that should have been caught in testing, small failures that cascade into total loss when you're in space and can't send a repair crew. She's learned to appreciate the fragility of these missions, how much has to go right continuously for years to achieve the science goals. Every successful observation is a small miracle of engineering persistence. The universe keeps turning while she thinks these thoughts, Earth orbiting the Sun, the Moon orbiting Earth, and at 5 invisible points in that dance, humanity maintains its tenuous presence, watching and measuring and trying to understand. The next story is about to begin. Please relax and enjoy. A lone spacecraft approaches one of Saturn's smaller shepherd moons, designation S47, a tumbling fragment barely 15 kilometers across that dances at the outer edge of the ring where ice crystals catch starlight like scattered diamonds. The mission parameters are simple. Collect samples from the ancient surface, map the gravitational anomalies that shouldn't exist in something so small, and return before the narrow launch window closes in 48 hours. But as the landing module touches down on the spongy fractured regolith, the geologist notices something impossible in the spectrometry readout. Organic compounds, complex chains that mirror the signatures detected in Enceladus's plumes 200 million kilometers away, and beneath them a thermal gradient suggesting the moon isn't the dead rock everyone assumed. The pilot wants to leave immediately, stick to the timeline, but the geologist convinces her to deploy the deep drill. Just one borehole, and what comes up in the core sample changes everything. Layers of water ice mixed with salts and amino acids, and stranger still, microscopic chambers in the ice matrix that look almost cellular, almost purposeful. They're not alone out here, not in the way anyone expected, and the question becomes whether they're looking at contamination from Enceladus's distant fountain, or whether something about Saturn's system, the constant exchange of material between rings and moons, the electrical currents that thread through the magnetosphere, the patient stirring of tides across billions of years, has created not one place where the chemistry of life can begin, but many scattered across dozens of small worlds that brush against each other in the dark. Back on the ship, analysing the samples in the cramped laboratory, they discover the organic structures aren't quite like anything in Earth's tree of life, but they're not entirely alien either, as if the recipe is universal, but each kitchen adds its own variations, and the pilot makes the call that will end her career or make it legendary. They're not going home on schedule. They're going to spend their remaining fuel budget visiting 3 more shepherd moons, checking whether this is an isolated anomaly, or whether Saturn has been running a quiet experiment in prebiotic chemistry right under humanity's observations for 50 years. The second moon yields similar results, but the structures are more complex, almost like they've had more time to develop, and the third moon, which orbits just inside the E-ring where Enceladus's ice grains fall like snow, shows clear evidence of layered deposits, each ice fall bringing new organic material, new possibilities, building up sediments of potential over geological time. By the fourth moon they're running on fumes and emergency reserves, and what they find isn't just chemistry anymore but something that might be metabolism, icebound pockets where chemical gradients drive slow reactions that look almost like breathing. and the geologist realizes they're looking at the earlier stages of something profound. Not life exactly, but pre-life, the patient assembly of components in a freezer that paradoxically preserves and enables complexity, because molecules don't break down in the cold, they just wait, accumulating in higher and higher concentrations until the threshold is crossed. But there's a problem, several problems actually, starting with the fact that they no longer have enough fuel to make the journey home, and ending with the fact that Earth needs to know about this immediately, not in 5 years when the next mission arrives, because if this is happening at Saturn, then it's probably happening at Jupiter too, round Europa and Ganymede where the conditions are even better, and maybe it's happening in the Uranian system and around Triton and in the sub-ice oceans of 100 Kuiper Belt objects that haven't even been discovered yet, which means the solar system isn't mostly empty space with a few pockets of interest. It's a garden, or a laboratory, or a network of connected experiments all running in parallel. They send the data burst, compress everything they've learned into a tight beam transmission aimed at Earth, knowing it will take over an hour to arrive and years to be fully understood, and then they make the decision that nobody trains for in mission simulations. They're going to crash land on Enceladus, use the last of their fuel to match orbits with the one moon in the system that's definitely active, definitely connected to the processes they've been observing, and if they survive the landing, a long shot given that the terrain near the tiger stripes is fractured and unstable, they'll have front row seats to the source. The descent is controlled chaos, the ship's heat shield ablating as they punch through the thin atmosphere of ejected particles, the surface coming up fast, too fast, and the pilot pulls off a miracle, skidding across smooth ice plains before coming to rest in a field of ice boulders 3 kilometers from the nearest active vent. They have life support for 6 days, no way to launch, no rescue possible for years, but they have instruments, curiosity, and the knowledge that they're standing on the most important square meter in the solar system. The first EVA takes them to the edge of a tiger stripe, where the ice is young and blue and fractured into geometric patterns that reveal the stresses below, and they can feel the moon breathing, not metaphorically but literally, rhythmic pulses of pressure as tidal forces squeeze and release the interior, and in the cracks they see fresh ice constantly forming, crystallizing from below, bringing up dissolved minerals and organics in concentrations that make the Shepherd moon samples look dilute. They collect everything they can carry, knowing each sample is irreplaceable, and as they work, the geologist starts sketching a theory. What if Enceladus isn't unique? What if it's the beating heart that supplies the entire system? The plumes carrying pre-life chemistry out into the E-ring, where it gets deposited on every moon that crosses the band, seeding them all with the same starter kit, and over time, millions or billions of years, each moon develops its own variation depending on its composition, its orbit, its tidal heating, creating not separate experiments, but connected ones, a network where success on one world can propagate to others. The pilot isn't convinced, argues that the chemistry is too fragile, that radiation and vacuum would destroy anything complex before it could spread, but the geologist counters with the ice itself. Each grain is a tiny spaceship, frozen solid, protecting its cargo for the years or decades it takes to drift from moon to moon, and maybe that's exactly the timescale that matters, not the quick chemistry of warm worlds, but the patient accumulation of cold ones. They spend days analysing samples in the ship, running every test they can improvise, and the patterns become clearer. The organic compounds aren't random, they're structured, they're selecting for stability and complexity, they're building towards something, and the question stops being whether this could lead to life and becomes how long until it does. On the 5th day, the pilot picks up a signal, faint and scattered, someone else in the system, and when they decrypt it, they discover it's a Europa mission that launched 2 years ago, just arrived, and they're seeing the same things: organic chemistry in the ice, thermal vents at the seafloor, signs of chemical gradients that look biological even if they're not, and suddenly the two crews are comparing notes across the gulf between Saturn and Jupiter, realizing that they're documenting the same process at different stages, Europa further along because the ocean is deeper and warmer, Saturn still in the early phases but with more worlds participating, and together they start building the bigger picture. By the 6th day they're running out of air and out of time, and the geologist records a final message, not for the rescue mission that might come in 3 or 5 or 10 years, but for whoever finds their data cache. Keep looking at the small moons, the ones everybody ignores because they're too small to have interesting geology, too cold to have interesting chemistry, because that's where the real story is. In the quiet exchange of materials, the patient cycling of ice and organics, the way Saturn's rings act as a distribution system spreading ingredients from the active moons to the dormant ones, creating a system-wide metabolism that operates on timescales humans barely comprehend. They seal the data in a hardened capsule and place it in the ice near the ship, and then they do the only thing left. They walk out across the ice plains toward the nearest active vent, carrying their instruments, observing until the end, and as they approach the vent, the pilot notices something the geologist missed. Tiny structures in the ice around the fractures. Patterns that look almost like colonies, like communities of chemical reactions that have organised themselves around the energy source. And she realises they're not just observing pre-life anymore. They're observing the threshold, the moment when chemistry becomes something else, something that responds to its environment, something that propagates, something that might, given enough time and enough moons and enough exchanges of material across the rings, become what humanity would recognise as alive. The last transmission is just coordinates and a single line. We found the garden, and it's bigger than we thought, and as the signal fades, the 2 crew members stand at the edge of the vent watching the plume rise kilometres into the black sky, carrying with it the raw materials of biology, spreading them across Saturn's system like seeds in a cosmic wind, and somewhere in orbit their ship's automated systems are still recording data, still measuring the flux of organics, still documenting the quiet mechanics of how worlds share their chemistry, and on Earth the first fragments of their transmission are being decoded, and teams are already planning new missions, faster ships, better instruments, because humanity has just learned that the solar system isn't a collection of isolated worlds but a connected network, a web of relationships where moons talk to each other through rings and plumes and the slow traffic of ice grains. And the question is no longer whether life exists beyond Earth, but how many different experiments are running simultaneously, how many different pathways are being explored, how many quiet gardens are growing in the cold dark places that orbit the giant planets, waiting patiently for someone to notice them. 3 years pass before the rescue mission reaches Saturn, and in that time the data from the lost crew transforms everything humanity thought it knew about the outer solar system, not just confirming that organic chemistry is widespread, but revealing patterns that suggest the process isn't random at all, that there's something almost orchestrated about the way materials flow between worlds, the way certain shepherd moons seem to act as reservoirs while others function as mixing chambers, the way the ring system itself appears to sort particles by size and composition in ways that maximize distribution efficiency. And while nobody is suggesting intelligence or design, the mathematics of it are elegant enough to make physicists uncomfortable. The rescue ship arrives with a crew of 12, not 2, and their mission parameters have expanded exponentially. Retrieve any remains, recover all data storage, and most critically, establish a permanent research station on Enceladus, because the political and scientific consensus is that humanity can't afford to study this phenomenon in brief flybys anymore. That understanding the origin of life, or the multiple origins of life, or the continuous creation of almost life, requires patient observation measured in years, not days. They find the original ship exactly where the automated beacon said it would be, partially buried in ice accumulation, and inside the data cores are intact, filled with observations that the crew kept recording even as their oxygen ran low, detailed measurements of plume composition variations, thermal maps of the tiger stripes showing how the vents pulse in response to Saturn's tidal cycle, and most hauntingly a series of microscope images showing the progressive organisation of organic compounds around energy gradients, like watching evolution in fast forward, except it's not evolution yet, it's the prelude, the sorting and testing that comes before natural selection has anything to select. They don't find bodies, not at first, but 3 kilometres away near the coordinates from the final transmission, they discover 2 suits, sealed and positioned carefully, as if the occupants simply decided to become part of the landscape they were studying, and when the recovery team opens the suits carefully, reverently, they find them filled with ice samples, dozens of vials and containers packed around the life support systems, a final act of scientific dedication that makes the rescue crew weep inside their helmets because they understand exactly what it means. These 2 people chose to turn themselves into cargo containers, to preserve one more set of irreplaceable observations, even if they couldn't survive to analyse them. The samples are extraordinary, showing a progression of complexity that the crew must have been tracking in their final hours. and among them is a vial labelled simply Threshold that contains structures so organised, so responsive to their chemical environment, that the mission's biologist refuses to classify them as non-living, inventing instead a new category she calls proto-animate, to describe chemistry that has crossed some invisible line into intentionality, into persistence, into something that wants to continue existing, even if it doesn't yet know how to reproduce. The research station goes up quickly, prefabricated modules anchored into stable ice with deep pylons, and within weeks they're operational, running experiments around the clock. And the first discovery is that the tiger stripes aren't static features, but dynamic, shifting slightly in response to tidal stress, opening new vents and closing old ones in a rhythm that repeats every Saturn orbit. And someone realizes that this rhythm itself might be crucial, that the periodic exposure to vacuum and radiation when vents seal might actually be part of the selection process, weeding out fragile chemistry and preserving only the structures robust enough to survive dormancy. They start mapping the entire E-ring in detail, tracking individual ice grains as they spiral outward from Enceladus, and they discover what the original crew suspected. The ring isn't uniform, it's structured, with distinct bands carrying different organic signatures depending on which vent they originated from. And the shepherd moons don't just randomly accumulate this material, they preferentially capture certain bands based on their orbital resonances, which means each small moon is receiving a curated selection of chemistry, not a random sample, and over geological time this non-random distribution could lead to different evolutionary experiments on different worlds, each starting with a slightly different toolkit. The implications spiral outward faster than anyone can track them. If this is happening at Saturn, then Jupiter's system must be even more complex, with Io's volcanic output adding sulfur chemistry to Europa's water, and Ganymede's magnetic field creating unique radiation environments that might drive entirely different reaction pathways. And someone points out that this means the Galilean moons aren't just 4 interesting worlds, they're 4 connected laboratories, running parallel experiments with slightly different initial conditions, and the results from one can propagate to the others through particle exchange and magnetic coupling. The Europa team, still operating in Jupiter's system, confirms this within weeks. They're detecting organic compounds in their ice cores that match Io's sulfur signature, mixed with native water chemistry in combinations that don't occur naturally on either world alone, which means the moons are collaborating, exchanging notes in a language written in chemistry and electricity. And the timescale for this exchange isn't human, it's geological. Millions of years of patient trading that has built up a chemical complexity neither world could achieve alone. Someone on the research station starts calling it the slow internet, and the name sticks. A network of worlds communicating through physical exchange of materials, through magnetic field interactions, through the gradual redistribution of particles by ring systems and plasmatoruses, operating on bandwidths measured in grams per century, but with a data capacity that spans billions of years. And the question becomes whether this network has been running since the solar system formed, or whether it took time to establish. Whether there was a moment when the first organic molecules from one world reached another and found conditions suitable for survival, bootstrapping a process that has been accelerating ever since. The research team starts looking at older data with new eyes, re-examining images from the Voyager flybys in the 1980s, and they find evidence that the tiger stripes were active even then, probably active for millions of years before that, which means Enceladus has been seeding Saturn's system for geological ages. And if the process is that old, then some of the shepherd moons might contain not just proto-life, but actual life. Organisms that have had millions of years to evolve in their tiny, frozen niches, and suddenly the mission profile changes again. They need to visit those moons with sterile equipment, need to be careful not to contaminate them with Earth life, or disrupt whatever processes might be unfolding there, and the ethics committees back home start arguing about whether humanity even has the right to study these worlds if they're already occupied, whether observation itself is a form of interference that could derail experiments that have been running since before humans existed. But the argument is academic because the missions are already launching, a fleet of small probes designed to visit every significant moon in Saturn's system with minimal contact, just spectroscopy and magnetic field mapping and particle collection. And what they find is staggering. Organic chemistry on every single world that spends time in the E-ring, increasing complexity correlated with proximity to Enceladus and with the duration of exposure, and on 3 of the smallest shepherd moons, the ones that orbit directly through the densest part of the ring, they find chemistry that's definitely animate. Microbial colonies living in ice-bound pockets, metabolizing sulfur compounds and perchlorate salts, and producing waste products that other colonies consume, creating little ecosystems barely visible under the highest magnification, but unmistakably alive, unmistakably structured, unmistakably doing what life does, persisting, adapting, spreading to every available niche. The discovery breaks across Earth like a wave, not the distant possibility of life on Mars, or the theoretical oceans of Europa, but actual, confirmed living organisms in Saturn's system, and the philosophical implications are immediate. Life isn't rare. It's not a fragile accident that requires perfect conditions. It's a natural consequence of chemistry plus energy plus time, and if it emerged in Saturn's system despite the cold and darkness and radiation, then it probably emerged in Jupiter's system too, and probably in the Uranian system, and probably around Neptune, and probably in the subice oceans of large Kuiper belt objects, and probably around other stars, and the Fermi paradox suddenly seems less paradoxical, because maybe the galaxy isn't silent. Maybe it's just that life spends its first billion years in places like this, quiet and cold and patient, and most of it never makes it to the stage where it builds radio telescopes. But that doesn't mean it's not there, not thriving in its own slow way, not mattering in the cosmic scheme. The research station on Enceladus becomes the most important scientific facility in human history overnight, and the crew expands to 30, then 50, then 100 as modules and supplies arrive on every available trajectory, and they start building outposts on other moons, on Titan where the methane seas might host entirely different chemistry, on Iapetus where the dark material coating one hemisphere might be organic fallout from ancient impacts on Hyperion whose spongy interior might harbour protected pockets of ancient ice with their own fossil record, and each outpost becomes a node in a growing human network that mirrors the slow internet they're studying. Information flowing between stations, observations building on each other, patterns emerging from the collective data that no single team could see alone. The geologist theory, recovered from the data cores, becomes the framework everyone uses. Enceladus is the heart. The shepherd moons are the circulatory system, the E-ring is the bloodstream, and every world in Saturn's system is an organ with its own function, its own contribution to the larger metabolism, and just as no single organ in a body can be understood in isolation. No single moon in Saturn's system can be understood without reference to all the others, to the flows of material and energy that connect them, to the history they share and the future they're building together. Someone calculates that if the process continues at its current rate, if the complexity they're observing keeps increasing, then in another 10 million years, some of these moons might host not just microbial colonies, but actual ecosystems with specialized organisms, maybe even something like multicellular life. And in 100 million years, who knows, maybe intelligence, maybe civilizations that will look up at their ringed sky and wonder what's out there, never guessing that their world and its neighbours are all part of a single, interconnected system that has been growing and evolving since before their planet's current orbit was established. The research teams start finding evidence of cycles, periods of high activity when Enceladus's plumes are stronger, followed by quiet periods when they nearly cease, driven by orbital eccentricities that vary over thousands of years, and they realise that these cycles themselves might be part of the selection process, that life in this system has to be adapted to feast and famine, to boom and bust, to waiting through dark periods and exploding during bright ones. And maybe that's another reason why it's so robust, because anything that survives here has already been tested by the harshest conditions imaginable. The Titan station starts reporting strange readings from the methane lakes, organic compounds at the bottom of Kraken Mare that look biological, but use a completely different solvent system than water-based life. And suddenly, there are two separate biospheres in Saturn's system, one based on water and ice, and one based on liquid hydrocarbons. And the question is whether they're related, whether organic material from Enceladus can rain down through Titan's atmosphere and seed the lakes below, whether there's exchange happening not just between water moons but across fundamental chemical divides, and if so, what kind of hybrid chemistry might emerge where the two systems overlap. The Jupiter team sends an update. They've found life on Europa, confirmed and undeniable, living in the ocean under the ice, and it's related to the life in Saturn's system. sharing enough genetic markers or chemical signatures that they must have a common origin, which means life doesn't just spread between moons within a single system. It spreads between systems, probably through asteroid impacts that launch material into solar orbit, and over billions of years those fragments can travel immense distances, can carry frozen organisms or at least frozen organic templates from Jupiter to Saturn to Uranus to Neptune and back again, making the entire outer solar system a single interconnected biosphere, a galactic-scale ecosystem held together not by proximity but by the patient exchange of materials across millions of years and billions of kilometers. The philosophical weight of this realization settles over everyone slowly. Humans aren't discovering life. They're discovering life with a capital L, not as a phenomenon that happens in isolated pockets, but as a fundamental characteristic of the solar system itself, something that emerges wherever conditions allow and spreads through every available pathway, limited only by time and distance and the basic requirements of chemistry. And if this is true for our solar system, then it's probably true for every solar system, which means the universe isn't mostly empty space with rare islands of life. It's mostly life with rare islands of emptiness, and everywhere there's matter and energy and time. The slow, grinding process of chemical evolution is working toward complexity, toward organization, toward something that eventually becomes aware of itself and starts asking questions about where it came from. The original pilot's observation, recovered from the final log entries, becomes the mission statement for everything that follows. We're not observers anymore, we're participants. We're part of the network now. Our ships and stations are nodes in the slow internet, and everything we do, every sample we take, every measurement we make, every piece of equipment we leave behind becomes part of the system's history, part of the data that future organisms or civilizations will have to interpret when they try to understand their own origins. And maybe that's okay, maybe that's inevitable, maybe the universe is full of civilizations that arose from chemistry that was accidentally cross-contaminated by previous civilizations, an infinite chain of influences stretching back to whatever the first life was, wherever it started, and maybe trying to be perfectly sterile is missing the point, because contamination is just another word for exchange, and exchange is how complexity grows, how systems become more than the sum of their parts. The research station on Enceladus celebrates its first full Saturn year of operation. 30 Earth years compressed into months of work that feels like decades, and they throw a party, awkward in low gravity, toasting with recycled water, while outside the plumes rise like clockwork, and someone says quietly that the original crew would have loved this, would have understood exactly what it means to watch the slow garden growing. And everyone is silent for a moment, thinking about the two explorers who gave everything to document the first evidence of the network, who became part of the ice they were studying, whose final samples are still yielding new discoveries 3 years later, and the station commander proposes a memorial. They'll place a marker at the coordinates where the suits were found, something permanent that will last for geological ages, and the inscription will be the geologist's final words from the data cache. Keep looking at the small moons, because that's where the real story is. And underneath, the pilot's final observation: we found the garden, and it's bigger than we thought. The marker goes up during the next EVA, a pyramid of machined titanium embedded deep in the ice, and around it they scatter some of the last samples the original crew collected, returning them to the environment they came from, completing a circle. And as they work, someone notices that the ice around the marker is already starting to develop the same patterns they've been observing elsewhere, the same organizing principles, as if the organic material in the samples is teaching the native chemistry new tricks. And maybe that's fitting. Maybe that's exactly how the network grows, through exchange and mixing and the patient accumulation of innovations that get passed from world to world, generation to generation, species to species, civilization to civilization, until the distinction between native and foreign stops mattering because everything is connected, everything is related, everything is part of the same ancient experiment that began when the first organic molecules formed in the first protoplanetary disk and has been running ever since, spreading through every available pathway, turning the universe slowly, patiently, inexorably into a garden. The 5th year of operations brings the first evidence that the network extends beyond what anyone imagined. When a research team analysing meteorite impacts on the outer Shepherd moons, discovers organic signatures that don't match anything in Saturn's system, compounds with isotope ratios pointing to origins in the Kuiper belt, frozen travellers that spent millions of years crossing the outer solar system before finally arriving here, and the implications cascade outward, like rings from a stone dropped in still water. If material from the Kuiper belt can reach Saturn's moons, then material from Saturn's moons can reach the Kuiper belt, and material from Jupiter can reach both, and suddenly the slow internet isn't just connecting the moons of individual planets, but linking every icy world in the solar system into a single vast web of chemical exchange that's been operating since the solar system's formation. The team starts modelling the trajectories, calculating how long it takes for material ejected from Enceladus's plumes to escape Saturn's gravity well, how it spreads through interplanetary space, how some fraction of it eventually collides with other worlds, and the numbers are staggering. Over the 4 billion years since the solar system stabilised, trillions of ice grains have made the journey from each active world to every other world, carrying their cargo of organic chemistry, their frozen libraries of molecular information, and even though the vast majority are lost to space or fall into the sun, or impact airless bodies where nothing can use them, the tiny fraction that lands in favourable environments is enough, given geological timescales, to seed the entire solar system with the products of every successful chemical innovation that's ever occurred anywhere. They find confirming evidence in the Kuiper belt data from the New Horizons extended mission, spectroscopic signatures on distant dwarf planets that match compounds first identified in Europa's ocean, and the researchers realise with mounting astonishment that they're looking at a postal system that's been running for billions of years, letters written in chemistry mailed from world to world at speeds measured in kilometres per second, taking millions of years to arrive, but arriving nonetheless, and every recipient world that has the right conditions can read those letters, can incorporate the information they contain, can build on it and send new letters of its own. The philosophical implications keep expanding. If the solar system is one connected network, then other solar systems must be networks too, and over the immense stretches of galactic time, material ejected from one star system can eventually reach others. Panspermia, not as a rare accident, but as an inevitable consequence of stellar dynamics and the sheer patience of frozen chemistry. And maybe that's why life uses the same basic molecules everywhere researchers look. The same amino acids and nucleotide bases and lipid structures, not because these are the only possible solutions, but because they're the solutions that worked in some ancient system billions of years ago and have been spreading ever since, copied and modified and adapted but still recognisably descended from whatever the first successful chemistry was, wherever and whenever it emerged. The research program expands again, this time looking at the very oldest ices they can find, samples from the most ancient surfaces where material has been accumulating since the solar system formed, and in a preserved layer on one of Saturn's most distant irregular moons, captured long ago from a different orbit, they find organic compounds that predate the solar system itself, interstellar molecules that survived the nebula's collapse and the violent early period when planets were still forming. And these molecules carry their own story, hints of chemistry that occurred in the stellar nursery before there were planets at all, and someone realises they're looking at evidence of pre-solar networks, chemistry that was already sophisticated when the sun was born, that came from previous generations of stars and planetary systems, an inheritance that goes back not just billions of years but potentially to the earliest epochs of the galaxy. A xenobiologist on the station starts calling it the galactic genome, the accumulated chemical knowledge of every successful origin of life that's ever occurred in the Milky Way, preserved in frozen grains that drift between stars, and while the information density is low and the transmission time is measured in millions of years and the error rate is astronomical, the system has been running for 10 billion years, and that's enough time for even the slowest network to build up a substantial library, to spread successful innovations across vast distances, to create a kind of chemical culture that transcends individual worlds and systems, and even individual epochs of star formation. The team starts looking for patterns in the distribution of organic compounds across different solar system bodies, trying to identify which innovations arose locally and which were imported, and they discover something unexpected. Certain complex molecules appear everywhere, on every world with the right conditions, but they always appear in the same sequence, as if there's a natural progression, a chemical ladder that systems climb one rung at a time, and this suggests that the evolution from simple organics to proto-life isn't random but follows predictable pathways constrained by thermodynamics and reaction kinetics, which means that anywhere in the universe with the right raw materials and energy sources is probably climbing the same ladder, possibly at different speeds, but following the same basic route. They test this hypothesis by examining the timeline of chemical evolution on different Saturn moons, comparing the progression on shepherd moons that have been in the E-ring for different durations, and the pattern holds. Younger exposures show simpler chemistry, older exposures show more complex chemistry, and the sequence is consistent, suggesting that given enough time and material input, all of these systems will eventually reach the same endpoint, whatever that endpoint is, whether it's simple self-replicating chemistry or something more complex, something that might deserve to be called alive. The implications for the search for extraterrestrial intelligence shift dramatically. If simple life is essentially inevitable given the right conditions, and if those conditions are common, and if life follows predictable pathways, then the question isn't whether aliens exist, but what stage different worlds and systems have reached in their chemical evolution, and whether there are predictable barriers or filters that prevent most systems from progressing beyond certain points, and what it means that Earth somehow passed those filters while presumably countless other worlds didn't. A theoretical biologist proposes what she calls the patient universe hypothesis, that the galaxy is full of worlds at every stage of chemical evolution, from the simplest organic compounds to proto-life, to simple organisms to complex ecosystems to intelligence. And the distribution follows a predictable curve with vast numbers at the simple end and progressively fewer at each stage of increasing complexity, not because the later stages are impossible, but because they take time, enormous amounts of time, and most worlds simply haven't had enough time yet, and Earth's intelligence is either a statistical fluke, arriving unusually early, or there's something about Earth-specific conditions that accelerated the process beyond the typical rate. The research station starts receiving data from the first dedicated Uranus mission in decades, and the findings confirm the pattern. Uranus's moons show the same kind of chemistry, the same progression of complexity correlated with exposure to material from active sources, and while Uranus doesn't have an Enceladus equivalent that's currently active, there's evidence that Miranda was geologically active in the past, possibly seeding the system during that period, and even now material arrives from interplanetary space, from other systems, keeping the slow chemistry working even in the absence of a local source. The Neptune data follows within months. Triton, captured from the Kuiper belt and still geologically active with its nitrogen geysers, is running its own version of the experiment, and the chemistry there is sufficiently different, influenced by nitrogen rather than water as the primary volatile, that it represents a parallel pathway, a different solution to the same basic problem of how to build complexity in a cold environment, and the researchers realize they're not looking at one way to make life but many, a whole space of possibilities that different worlds explore depending on their specific conditions, and maybe that's the real answer to why the universe seems so empty of radio signals, because most life doesn't follow the same pathway Earth did, doesn't emerge in warm oceans under thick atmospheres on rocky planets in habitable zones, but emerges instead in cold oceans under ice shells in systems where sunlight is irrelevant and the energy comes from tides and radioactivity, and those systems don't build radio telescopes because they don't have access to fire or metallurgy, or any of the technologies that require atmospheric chemistry, but they might still be alive, still conscious, still wondering if they're alone. Someone points out that humanity's presence in Saturn's system is itself becoming part of the network now, that the research stations are shedding organic compounds and metabolic byproducts, that the ships landing and taking off are distributing Earth chemistry across the moons they visit, and while the teams are trying to minimize contamination, complete sterility is impossible, which means in 1,000,000 years some future system, whether it's evolved from native Saturn chemistry, or from Earth contamination, or from some hybrid of the two, will find traces of human presence in the ice record and will have to interpret them. We'll have to decide whether these strange compounds indicate natural processes or artificial ones. And maybe they'll never know that they're the descendants, direct or indirect, of a process that humans accidentally accelerated by their simple presence. The ethical debates intensify. Should humanity try harder to prevent contamination? Should they abandon the research stations to preserve the natural evolution of Saturn's chemistry? Or is contamination inevitable and possibly even beneficial, a way of accelerating the slow internet? of providing new information to systems that might be able to use it, and maybe the whole concept of contamination is anthropocentric anyway, based on an outdated idea that each world's chemistry should be pristine and separate, when the reality is that worlds have been exchanging chemistry for billions of years, and Earth's contribution is just one more voice in an ancient conversation. The station commander makes a decision that surprises everyone. They're going to stop trying for perfect sterility. They're going to accept that humans are now part of Saturn's system, part of its metabolism, and instead of fighting that reality, they're going to study it, monitor how Earth chemistry interacts with native chemistry, see whether the hybrid systems that result are more or less complex than either parent system alone, treat the human presence as an experiment in accelerated exchange, in what happens when systems that evolve separately suddenly have access to each other's innovations, and maybe the results will tell them something important about how the slow internet works, about whether exchange always increases complexity, or whether there are conditions under which it causes interference instead. The next story is about to begin. Please relax and enjoy. The rain begins softly, a whisper against the window, and you stand beneath clouds so thick the afternoon feels like dusk. You know that above this grey ceiling, beyond the atmosphere's veil, there are not just stars, but suns. Countless furnaces of light, each burning with its own colour and tempo, each setting the rhythm for worlds you will never touch. Some blaze blue and fierce, living fast and bright. Others glow dim red, patient enough to outlast empires, galaxies, perhaps even time itself. And somewhere among them, on a world you cannot name, beneath a sky lit by a sun nothing like your own, someone might be standing as you are now, watching rain fall, wondering what lies beyond their clouds. In the cold depths between those distant suns, where starlight fades to nothing and the void stretches dark and infinite, there are clouds of a different kind. Molecular clouds, they're called. Great drifting masses of gas and dust, cold enough to freeze thought itself. Within these clouds, gravity works slowly, patiently, gathering material into knots the way a river gathers silt. Over millennia, these knots contract. The material falls inward, pulled by its own weight, and as it falls, it heats. Not quickly, not with flame or violence, but with the slow warmth of compression, the way your hands warm when you press them together. At the heart of each knot, something begins to glow, a protostar, barely visible through its cocoon of dust, surrounded by a disk of spinning material that will one day become planets, moons, asteroids, perhaps even life. You cannot see this process, of course. It takes millions of years. But imagine it anyway. The dust grains in that disk colliding and sticking, building pebbles from sand, boulders from pebbles, worlds from boulders. Jets of gas flicker along magnetic field lines, carrying away excess energy. The disk flattens as it spins, a cosmic phonograph record with the protostar as its needle. And all the while, the core grows denser, hotter, its atoms pressing closer together, their dance becoming frantic. Pressure mounts, temperature climbs, and then, at some threshold that cannot be predicted to the second but is nonetheless inevitable, hydrogen nuclei begin to fuse. The star ignites, light steadies. Outward pressure from fusion balances the inward crush of gravity, and the star joins what astronomers call the main sequence, the long, stable middle age during which most stars spend most of their lives. Where a star sits on that sequence depends entirely on its mass. Mass is destiny in the stellar world. A star with 10 times the sun's mass burns blue-white and fierce, exhausting its fuel in mere millions of years. A star with 1/10, the sun's mass glows dim red, and sips its hydrogen so slowly it could burn for trillions of years, longer than the current age of the universe, longer than any measurement of time that holds meaning for human minds. Between these extremes lie all the gradations, white stars and stars, yellow stars, orange stars and amber stars, each with its own rhythm, its own lifespan, its own way of shaping the space around it. When you look at a star, you are looking at a message written in light. That light, when passed through a prism or a spectrograph, splits into a spectrum, a rainbow marked by dark lines where specific wavelengths have been absorbed. These lines are fingerprints. Each element in the star's atmosphere absorbs light at particular wavelengths. Hydrogen leaves its marks, calcium its own, iron and sodium and helium each signing their presence in the starlight. By reading these lines, Astronomers determine what a star is made of, how hot it burns, even how fast it moves. If a star is approaching, its spectral lines shift slightly toward the blue, if receding, toward the red. Tiny shifts, but enough to reveal motion across the galaxy, enough to detect the gravitational tug of unseen planets pulling their stars into subtle wobbles. Most of the suns in the galaxy are red dwarfs, small, cool, patient M-type stars that make up perhaps 70% of all stars, but contribute almost nothing to the visible light of the night sky. They are too dim to see without telescopes, most of them, but they are everywhere, scattered through space like seeds. A red dwarf might burn for 10 trillion years, releasing its energy so slowly that the universe will have changed beyond recognition before it finally exhausts its fuel. Their habitable zones, the orbital distances where liquid water could exist on a planet's surface, are close in, so close that planets there are likely to be tidally locked, showing the same face to their star forever, one hemisphere in eternal day, the other in eternal night. And red dwarfs are restless. Their magnetic fields churn and twist, producing frequent flares that flood their inner systems with radiation. Any world in the habitable zone of a red dwarf must endure this flickering violence, this temperamental light that might strip atmospheres away, or perhaps drive evolutionary pressures toward resilience. A step up in mass and you find K dwarfs, orange stars that glow soft and steady, cooler than the sun but not as cool as red dwarfs, longer lived but not as patient. K-type stars offer a middle path. They burn for tens of billions of years, long enough for countless chances at complexity, yet they are calmer than their smaller siblings, less prone to violent flares. Their light is warm, autumn-tinted, and their habitable zones are wide enough, stable enough, that planets there might enjoy billions of years of gentle, predictable daylight. Time enough for oceans to form and life to experiment, to fail, to try again. Then there are stars like the Sun, G-type yellow dwarfs that sit in a comfortable middle range. The Sun has been burning steadily for 4.5 billion years and has another 5 billion to go before it exhausts the hydrogen in its core. That is enough time for continents to drift, for species to rise and fall, for intelligence to emerge and wonder at the stars. G-type stars provide steady, bright light without the intense ultraviolet radiation of hotter stars or the temperamental flickering of cooler ones. They are Goldilocks stars, not too hot, not too cold, and their habitable zones are wide enough that planets can orbit at comfortable distances, spinning freely, enjoying day and night in regular cycles. But go higher in mass, and you find the fast burners, the A, B, and O stars that blaze white and blue. These are the stars that dominate star-forming regions, that sculpt nebulae with their fierce winds and ultraviolet light. They pour out energy at staggering rates, living only millions of years, sometimes only a few million, before exhausting their fuel. Around such stars, planets would be drenched in UV radiation, their atmospheres stressed, their surfaces harsh. There is little time for the slow work of evolution in such systems. By the time a world might settle into stable rhythms, its sun is already dying. All stars die, of course, but they die in different ways. When a star like the Sun exhausts the hydrogen in its core, fusion slows and gravity begins to win again. The core contracts, heats, and hydrogen in a shell around the core begins to fuse instead. This shell burning drives the outer layers outward. The star swells into a red giant, its surface cooling and reddening even as its core grows hotter. Red giants are gentle in a way, luminous but diffuse, their outer layers so tenuously held that stellar winds carry gas into space, enriching the interstellar medium with elements forged in the star's interior. Carbon, nitrogen, oxygen, ingredients for future stars and planets, drift outward in slow exhalation. Some giants pulse, their outer layers expand and contract in regular cycles, driven by instabilities in the way light moves through those enormous cool atmospheres. Cepheid variables pulse with periods measured in days or weeks, their brightnesses varying so predictably that astronomers use them as cosmic yardsticks, measuring distances across the galaxy. Our Lyrae stars pulse faster, with periods of hours. Mira-type giants pulse slowly, over months or years, their variability visible even to ancient watchers who saw them flare and fade in the night sky, mysterious breathing lights. Most stars are not alone. Perhaps half of all sun-like stars, maybe more, are in binary systems, two stars orbiting a common centre of mass. Some binaries are wide, the stars separated by hundreds of astronomical units, each evolving independently. Others are close, their mutual gravity reshaping them. In some systems, one star pulls gas from its companion, drawing material through an invisible bridge between them. This mass transfer changes both stars, altering their evolution, sometimes producing spectacular outbursts as stolen gas spirals inward and heats. In the closest binaries, both stars may be locked in tight embrace, whirling around each other in hours or days, their surfaces nearly touching, their atmospheres mingling. Stars are also born in families, open clusters, loose gatherings of a few hundred to a few thousand stars, form together in molecular clouds, and then drift apart over tens or hundreds of millions of years. Globular clusters are older, denser, ancient spheres containing hundreds of thousands, or even millions of stars, relics from the early galaxy, orbiting the Milky Way's halo like loyal attendants. Because all the stars in a cluster formed at roughly the same time from the same material, clusters are laboratories for understanding stellar evolution. The most massive stars have already died. The smallest are still burning. By studying which stars remain and which are gone, astronomers piece together timelines of stellar life. Within each star's light is a record of its birth. Astronomers call elements heavier than helium metals, regardless of what they actually are. Carbon, oxygen, iron, all lumped together under that term. A star's metallicity tells you when it formed. The first stars, born in the pristine hydrogen and helium left over from the Big Bang, had almost no metals at all. When those stars died, they scattered heavier elements into space. The next generation of stars formed from slightly enriched gas. With each generation, the metallicity increased. Today's stars, formed from clouds enriched by billions of years of stellar death, carry the signatures of countless previous lives in their spectra. Low metallicity stars are ancient voyagers, time capsules from the early universe. High metallicity stars are recent arrivals built from the ashes of many predecessors. Stars also have weather. Rotation and convection in a star's outer layers generate magnetic fields, and those fields erupt through the surface in complex patterns. Sunspots are magnetic knots where the field suppresses convection, cooling the surface and creating dark patches. Flares are sudden releases of magnetic energy, flooding space with radiation and particles. Coronal mass ejections hurl billions of tons of plasma outward at high speed. All of this affects any planets orbiting the star. Planetary magnetic fields channel these particles toward the poles, producing auroras, curtains of light in the upper atmosphere. Over time, stellar winds can erode atmospheres, especially on planets without strong magnetic shields. The star's weather becomes the planet's destiny. We find those planets by watching the stars. When a planet crosses in front of its star from our perspective, the star's light dims slightly, a transit. By measuring the depth and duration of the dimming, astronomers determine the planet's size and orbital period. If the transit happens repeatedly, precisely on schedule, it confirms a planet is there. Sometimes, during a transit, starlight filters through the planet's atmosphere, and the spectrum of that light carries the chemical fingerprints of atmospheric gases, water vapour, methane, carbon dioxide. We are learning to read planetary atmospheres from trillions of miles away, to taste the air of worlds we will never visit. We also find planets by watching stars wobble. A planet's gravity tugs its star, pulling it into a small orbit around the system's centre of mass. As the star moves toward us and away, its spectral lines shift, Doppler shifts, the same effect that changes the pitch of a passing siren. By measuring these shifts over time, astronomers determine the planet's mass and orbit. Combined with transit data, this gives a complete picture: size, mass, density, orbit. Rocky worlds and gas giants, hot Jupiters hugging their stars and ice giants drifting far out, all revealed by the star's subtle dance. There are other methods, rarer but powerful. Direct imaging captures the light of giant planets orbiting far from their stars, young worlds still warm from formation. Gravitational microlensing detects planets by the way their gravity bends the light of a more distant background star, a fleeting alignment that might happen only once and never repeat. Astrometry tracks the star's position on the sky. measuring its motion over years or decades to reveal the pull of long-period companions. Each method has its strengths, its biases, its blind spots. Together, they map the diversity of planetary systems, and as we find these worlds, we ask, could they harbour life? The answer depends on their stars. A star's type sets the boundaries of its habitable zone, the range of distances where temperatures allow liquid water. Red dwarfs have narrow habitable zones close to the star, where planets might be tidally locked and battered by flares. K and G stars offer wider, calmer zones. Blue stars flood their surroundings with UV radiation and change too fast, dying before life has time to gain a foothold. But habitability is not just about water. It's about stability, about time, about the kind of light that falls on a world's surface and the rhythms that light imposes. Imagine standing on a planet orbiting a red dwarf. Noon might be copper-tinted, the sun a dim red disk hanging motionless in the sky if your world is tidally locked. One side of your planet bakes in eternal day, the other freezes in eternal night, and only in the twilight band between them, where winds howl from the heat toward the cold, might conditions be tolerable. Or imagine a world around a blue-white star, where daylight is icy pale and intense, where summers are fierce and brief, where the star's brightness fluctuates as it pulses through instabilities. The colour of daylight shapes vision, photosynthesis, the very chemistry of life. The length of day and year sets rhythms for behaviour, metabolism, sleep. All stars end. The smallest red dwarfs will burn until they have fused all their hydrogen, then cool slowly into hypothetical white dwarfs, a fate that awaits them trillions of years from now, so far in the future that it's uncertain whether the universe will still resemble anything we'd recognise. Sun-like stars swell into red giants, shed their outer layers as glowing shells called planetary nebulae, and leave behind white dwarf cores, Earth-sized embers, hot but no longer fusing, slowly cooling over billions of years. Massive stars die violently. When their cores run out of fuel, they collapse in milliseconds, triggering supernovae that outshine entire galaxies for weeks. These explosions forge the heaviest elements, iron, gold, uranium, and scatter them into space. The shock waves from supernovae compress nearby clouds, triggering new star formation. Death and birth intertwined, the galaxy recycling itself. Stars are also travellers. They form in nurseries, dense regions within molecular clouds, where dozens or hundreds of stars ignite within a few million years of each other. After birth, the stellar winds and radiation from the hottest stars disrupt the remaining gas, and the cluster begins to disperse. Some stars drift into loose-moving groups, sharing similar velocities as they orbit the galactic centre. Others scatter, becoming isolated field stars. The Milky Way is crisscrossed with stellar streams, trails of stars pulled from clusters or small galaxies by tidal forces, evidence of the galaxy's ongoing assembly. By mapping stellar motions, ages and compositions, astronomers reconstruct the Milky Way's history, tracing merger events, identifying in falling satellites, watching the slow churn of galactic evolution. The rain continues, steady now, and you think about how strange it is that you can know these things. That light, travelling for years or centuries or millennia, carries information encoded in wavelengths and intensities, and that human minds, evolved to navigate savannas and recognise faces, can decode that information, can reconstruct the lives of suns they will never see up close. Behind the clouds above you, the sun is setting, though you cannot see it. And beyond the sun, thousands of light years away, a red dwarf is flaring, its planets huddled close, their atmospheres straining. A K-type star rotates slowly, its habitable zone calm and wide, its world cycling through gentle seasons. A binary system exchanges gas in a glowing stream. A Cepheid variable swells and contracts, its light pulsing like a heartbeat visible across the galaxy. A blue supergiant burns through its final reserves, months or years away from its explosive end. You will never visit those places. No one alive today will. But you can know they exist. You can understand, in outline if not in detail, the forces that shape them, the physics that governs them, the timescales on which they change. You can look at the spectra of stars and read their compositions, their ages, their motions. You can watch a star dim and know a planet has passed in front of it. You can measure a star's wobble and calculate the mass of an unseen companion. These are not small achievements. They are evidence of something remarkable about intelligence, about curiosity, about the human refusal to accept the night sky as mere decoration. The galaxy is full of quiet hearts. Most stars burn unnoticed, too dim or too distant to catch the eye. They do not care whether anyone watches them. They fuse hydrogen into helium, helium into carbon, some of them carbon into heavier elements still, following the logic of nuclear physics with no awareness, no intention, no purpose beyond the balance of gravity and pressure. And yet they create the conditions for everything else. They forge the elements that make planets, atmospheres, oceans, life. They provide the energy that warms worlds, that drives weather, that powers photosynthesis and all the cascading complexity that follows. They set the clocks by which days and years are measured, the rhythms to which life adapts. You think about the first humans who looked up and wondered what the stars were. They made stories, connected dots into constellations, imagined the stars as distant fires or holes in the sky or the eyes of gods. They had no way to know the truth was stranger and more beautiful than any story, that each star was a sun, that some had planets, that those planets might have weather and seasons and perhaps even life, looking back across the light years with their own questions. For most of human history, the stars were unreachable, unknowable. Now we reach them with light. Spectroscopy and photometry, interferometry and astrometry, all the ways we've learned to extract meaning from photons that have travelled unimaginable distances. The rain is easing now, the clouds beginning to break. A patch of sky appears, still bright with late afternoon light. No stars visible yet, but they are there. They are always there. Tens of billions of them in this galaxy alone, each with its own story written in light, its own cycle of birth and death, its own contribution to the slow alchemy that turns hydrogen into everything else. Some are giants, luminous enough to be seen across the galaxy. Some are dwarves, invisible beyond a few light years. Some are young, still surrounded by the disks from which planets are forming. Some are old, white dwarfs cooling in the dark, or neutron stars spinning in silence, or black holes marking where the most massive stars once burned. And around some of those stars, around how many we still don't know, there are worlds. Rocky worlds and gas giants, ice giants and lava worlds, planets with thick atmospheres and planets with none. Worlds where volcanoes erupt under red light, where oceans freeze and thaw with the star's brightness, where storms rage for centuries, where surfaces are scoured by radiation or sheltered by magnetic fields. Worlds where maybe life has emerged, simple at first, perhaps staying simple, perhaps evolving into complexity, perhaps achieving intelligence, perhaps looking out at their own night sky and wondering, as you're wondering now, what lies beyond. You cannot know if anyone is out there looking back. The distances are too vast, the timescales too long, the chances too uncertain. But the question itself is worth holding. It changes how you see the rain, the clouds, the patch of clearing sky. It reminds you that you are standing on a planet orbiting a G-type star, that this star is one of hundreds of billions, that each of those stars has its own character, its own rhythm, its own influence on the space around it. It reminds you that the universe is not a static backdrop but a living system, constantly changing, constantly creating new conditions, new possibilities. The rain stops, the clouds drift east, the first stars appear, faint against the still bright sky, growing more visible as twilight deepens. You do not know which ones have planets, which ones are red dwarves or blue giants or yellow dwarves like the sun. But you know they are all suns, all burning, all shaping the worlds that orbit them. Their quiet hearts beat in fusion rhythms, setting the time for everything that happens near them, and their light, filtered through space and time, tells you their stories, stories written in spectra and brightness variations, in wobbles and transits, in the elements they forge and the winds they blow and the ways they change the darkness around them. You stand there a little longer, watching the stars appear, thinking about all those distant suns and the worlds that circle them, the rhythms they set, the possibilities they hold. The air has grown cold, the kind of cold that settles after rain, when moisture still clings to everything and the earth releases its stored warmth into the clearing sky. You can smell the wet pavement, the soil, the faint green scent of plants breathing in the dark. These are the smells of a world shaped by a particular star at a particular distance, with a particular atmospheric composition and magnetic field and axial tilt. Everything about this moment, the temperature, the oxygen you breathe, the water that just fell from the sky, exists because of where Earth sits in the sun's habitable zone, because of how the sun burns, because of what the sun is. But you are thinking beyond this world now. You are thinking about those planets around red dwarfs, where the habitable zone is so narrow that a planet must orbit its star in a matter of days or weeks, so close that tidal forces lock one face eternally toward the dim sun. On such a world, there would be no sunrise, no sunset, no daily cycle to mark time. The star would hang fixed in the sky, a dull ember casting long shadows, and everything would arrange itself according to that geometry. Weather patterns flowing from the hot side to the cold, ecosystems clustering in the twilight regions where temperatures are tolerable, evolution proceeding under constraints utterly unlike those on Earth. If intelligent life arose there, what would they make of their sky? Would they even think to look up? Or would their attention always be drawn horizontally toward the terminator where day meets night, toward the liminal spaces where their world is most habitable? And what of the planets around K-dwarfs, those patient orange suns? There, days and nights would cycle normally, but everything would happen more slowly, more gently. The star would live longer than the sun, offering more time for complexity to develop, for ecosystems to mature, for intelligence to emerge and build and wonder. The light would be warmer, more amber than Earth's sunlight, and photosynthesis might work differently there. Plants and algae tuned to a spectrum shifted toward the red. Autumnal light, year-round, never harsh, never scorching. A world like that might be gentler than Earth, its weather less violent, its seasons more measured. Or perhaps not. Perhaps the slower stellar winds would allow thicker atmospheres to accumulate, turning such worlds into pressure cooker greenhouses. Or perhaps the stability would breed stagnation, ecosystems settling into equilibria that resist change. You try to imagine what it would be like to live under a blue sun, an A-type or B-type star burning bright and hot. The light would be strange, pale and intense, flooding the world with ultraviolet radiation that would require any life to develop sophisticated protective mechanisms. Thick ozone layers, UV-absorbing pigments, perhaps living underground or underwater during the star's brightest hours. The star itself would be young, a few million or tens of millions of years old at most, and in another few million years it would begin its death throes, swelling and brightening and finally exploding. There would be no deep time on such a world, no billions of years for evolution to tinker and refine. Any life there would have to arise quickly, adapt quickly, live quickly, always under the ticking clock of the star's inevitable end. Perhaps that urgency would drive rapid evolution, or perhaps it would make complexity impossible, life never able to gain more than a fragile foothold before being erased. These thoughts lead you to consider the planets that orbit binary stars, those systems where two suns share the sky. Some of these systems are widely separated, with planets orbiting just one star while the companion shines as a brilliant point of light in the sky. A second sun that never rises or sets, just slides along its slow path through the constellations. But in closer binaries, planets might orbit both stars in figure-8 or circumbinary orbits, and there the sky would be truly alien. Two suns rising at different times, casting double shadows, their combined light shifting in colour and intensity as their orbits bring them closer and farther apart. Eclipses would be common, one sun passing in front of the other, the world plunged into partial darkness in the middle of the day. Seasons would be chaotic, unpredictable, governed not by axial tilt alone but by the complex gravitational dance of two stars pulling the planet along elliptical paths. What kind of life could evolve under such conditions? What kind of calendars would such a civilization develop? What kind of myths would they tell about their twin suns? The sky is darker now, the stars more numerous. You recognise a few constellations, Orion rising in the east, the Pleiades higher up, their clustered stars so young they still glow blue, having formed only 100 million years ago, cosmic infants. The Pleiades are sisters in more than mythology. They truly were born together, condensing from the same molecular cloud, and they still travel together through space, their motions linked. In a few 100 million years they will drift apart, scattered by gravitational interactions with other stars and giant molecular clouds, each sister going her own way, their family dissolved into the wider population of the galaxy. But for now they remain together, a visible reminder that stars have histories, relationships, origins. You think about the globular clusters you cannot see, those ancient spheres of stars orbiting the Milky Way's halo, each cluster containing hundreds of thousands of stars packed into a sphere only tens of light years across. The stars there are old, 10 billion years or more, formed when the galaxy itself was young. In the core of a globular cluster, stars are separated by only light weeks or light months instead of light years, and their sky would be filled with bright stars, hundreds of them as bright as Venus appears from Earth, the night never truly dark. But those stars are metal poor, forged before the galaxy had been enriched with heavy elements, and it is unclear whether planets could even form around them, whether there is enough silicon and iron and carbon to build rocky worlds. Perhaps life in globular clusters is impossible, or perhaps it is merely different based on chemistry we have not imagined. The thought of alien chemistry leads you down another path. Life on Earth is based on carbon, water, and a few dozen other elements, all forged in stars and scattered by supernovae. But the availability of those elements varies across the galaxy. Stars formed in the outer regions of the Milky Way, far from the dense star-forming regions of the spiral arms, are metal poor. Stars formed near the galactic centre, where star formation has been intense and supernovae frequent, are metal rich. Does this mean life is more common in some regions than others? Are there galactic habitable zones, not just stellar ones, regions where the density of heavy elements is high enough to form rocky planets, but not so high that the star formation rate produces too many supernovae, sterilizing nearby systems with gamma rays and cosmic rays? And what of the elements themselves? Every atom of carbon in your body was forged in the core of a red giant, where helium nuclei fuse together in the triple alpha process, a reaction so delicate that it requires a precise resonance. In the carbon nucleus, a quantum coincidence that seems almost designed to allow carbon's existence. Every atom of oxygen came from heavier stars, where neon and magnesium burning produced oxygen as a byproduct. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all of it created in the cores of massive stars, then ejected in supernova explosions, spreading through the interstellar medium, mixing with hydrogen and helium, eventually collapsing into new stars and new planets. You are quite literally made of stars your atoms cycled through multiple generations of stellar birth and death, before finally assembling into the form standing here under the clearing sky. This recycling is ongoing. Right now, somewhere in the galaxy, a star is exploding, and in the heat and pressure of that explosion, nuclei are being slammed together to create elements that do not exist elsewhere, elements heavier than iron like gold and platinum and uranium. Those elements will drift outward in an expanding shell of gas and dust, cooling as they go, eventually encountering a molecular cloud. The shock wave from the supernova will compress the cloud, triggering new star formation, and some of the heavy elements will be incorporated into the next generation of stars and planets. In this way, the galaxy gradually becomes more metal-rich over time, each generation of stars chemically distinct from the last, a slow enrichment that has been ongoing for more than 10 billion years. You wonder if there are planets where life developed earlier than on Earth, around stars formed when the galaxy was younger, its metallicity lower. Would such life be fundamentally different, working with a more limited palette of elements? Or would the same chemistry prevail, carbon and water and oxygen forming the backbone of biology everywhere, regardless of when the planet formed? And what of life that might develop later, billions of years from now, on planets around stars not yet born, formed from clouds enriched by countless more generations of supernovae? Would those organisms have access to heavier elements in such abundance that their biochemistry could explore possibilities unavailable to Earth life? The temperature continues to drop. You can see your breath now, faint wisps of vapour catching the last light from the western horizon. Water vapour, H2O, 2 hydrogen atoms and 1 oxygen atom, the former from the Big Bang, the latter from a long-dead star. This simple molecule, so common in the universe that it forms vast clouds in space, and ice mantles on interstellar dust grains, is the medium of life on Earth and likely on many other worlds. But water is strange. It expands when it freezes, making ice float, a property that keeps Earth's oceans from freezing solid from the bottom up, allowing life to persist through ice ages. It has a high heat capacity, moderating temperature swings. It is an excellent solvent, allowing the chemistry of life to proceed in liquid form. These properties are consequences of water's molecular structure, the way oxygen hogs electrons and gives the molecule a lopsided charge distribution, allowing water molecules to hydrogen bond to each other. Would alien biochemistry necessarily use water, or are there other solvents, ammonia, methane, even liquid methane on cold worlds like Titan, that could serve the same purpose? You shake your head, smiling at the way your thoughts spiral outward, each question leading to more questions, the universe revealing itself as infinitely more complex and strange than you can fully grasp. But that is the joy of it, is it not? That there is always more to learn, more to wonder about, that every answer opens new mysteries. The stars above you are not just points of light but puzzles, each one a laboratory, running experiments in nuclear physics, hydrodynamics, magnetohydrodynamics, each one producing conditions that do not and cannot exist on Earth. By studying them, by analysing their light and tracking their motions and modelling their interiors, astronomers are doing more than cataloguing the cosmos. They are learning the fundamental rules that govern matter and energy, the constraints within which everything, stars, planets, life intelligence, must operate. And now, finally it is fully dark, the clouds entirely gone, the sky a deep blue-black scattered with stars. You pick out a few more constellations, Cassiopeia, Andromeda, Perseus, and you remember that the faint smudge near Andromeda, barely visible to the naked eye, is not a star at all but another galaxy, M31, the Andromeda Galaxy, a spiral like the Milky Way, containing hundreds of billions of its own stars, its own molecular clouds, its own planets, and perhaps its own instances of life and intelligence. That galaxy is 2.5 million light-years away, meaning the light you see left there 2.5 million years ago, when the first members of the genus Homo were beginning to walk upright on the African savanna. You are seeing Andromeda not as it is now, but as it was then, and if anyone in Andromeda is looking back at the Milky Way, they are seeing it as it was 2.5 million years ago, long before humans existed. This time delay, this light travel time, means that the universe you perceive is not the universe as it exists in some objective now. There is no universal now. Every star you see is a message from the past, some more distant than others, and the farther you look, the further back in time you see. The most distant objects visible to telescopes, galaxies near the edge of the observable universe, are seen as they were more than 13 billion years ago, when the universe itself was young, when the first stars were just beginning to form. Those galaxies may no longer exist. Their stars long since burned out or collapsed into black holes, but their light is only now reaching us. Ghosts from a universe that no longer exists in the form we perceive. You turn your gaze back to the nearer stars, the ones you can see without a telescope. Sirius, the brightest star in the night sky, is only 8 light-years away, close enough that its light is recent, showing you the star almost as it is now. Betelgeuse, in Orion's shoulder, is a red supergiant, bloated and unstable, somewhere between 400 and 600 light-years away. When you see it, you're seeing it as it was in the 1400s or 1500s, during the Renaissance, and it is possible, unlikely but possible, that Betelgeuse has already exploded, that the shockwave and light from that explosion are racing toward Earth right now, unseen, and will arrive tomorrow or next year or 100 years from now, suddenly making Betelgeuse as bright as the full moon for weeks or months before it fades. No one knows when Betelgeuse will explode, only that it will, that it is near the end of its life, that its core is a tangle of fusion shells burning different elements, the star struggling to maintain equilibrium as gravity tries to crush it, and fusion pressure tries to blow it apart. When Betelgeuse does explode, it will be spectacular. For a few weeks it will outshine every other star in the sky except the Sun. Ancient records will be searched for omens and myths, new ones will be created, and astronomers will point every telescope on Earth and in space at it, capturing data about a supernova closer than any in recorded history. The explosion will create a neutron star or perhaps a black hole, and it will seed the interstellar medium with new elements, enriching the clouds from which future stars will form. And then, over tens of thousands of years, the ejected material will expand and cool and fade, leaving behind only a faint nebula and the compact remnant, and the constellation of Orion will be subtly different, one of its brightest stars gone, replaced by a dimmer point, a stellar remnant barely visible except in infrared or X-ray wavelengths, the ghost of a giant that once was. You realise that you have been standing outside for longer than you intended, that the cold has worked its way into your fingers and toes, but you are reluctant to go inside just yet. There is something about this moment, this particular arrangement of sky and thought and silence, that feels important to hold on to. The stars have always been there, of course, every night of your life, every night of every human life that has ever been lived. But how often do you actually look at them, actually think about what they are? How often does anyone? Modern life pulls attention downward and inward, to screens, to immediate concerns, to the small sphere of influence that defines daily existence. The stars become backdrop, decoration, something noticed only in passing, if at all. But they deserve more than passing notice. Each one is a story, a process, a set of conditions playing out over timescales that dwarf human comprehension. That red point of light low on the horizon might be a dying star, swollen and cool, in its last million years before shedding its outer layers. That white point might be a young star, still surrounded by a disk of planet-forming material, worlds coalescing from dust even now. That steady yellow point might be hosting a planet where rain is falling, where oceans are stirring, where something lives and moves and perhaps even thinks. You cannot know, the distances are too great, the observations too difficult. But the possibilities are there, written into the physics of stars and planets, statistical inevitabilities emerging from the vast numbers involved. The Milky Way itself is visible now, a faint band of light arching overhead, dense in some regions and sparse in others. You are looking edge-on into the disk of the galaxy, seeing the combined light of billions of stars too distant to resolve individually. The dark patches are not empty space but dust clouds, regions where new stars are forming, blocking the light of stars beyond. The brightest regions are the spiral arms, where star formation is most active, where massive blue stars light up their surroundings before dying young. The galaxy is rotating, all these stars orbiting the common centre where a supermassive black hole weighing millions of solar masses sits quietly, its gravity holding everything together. The Sun orbits that centre once every 230 million years or so, a galactic year, and it has completed about 20 such orbits since it formed. 20 trips around the galaxy during which continents have assembled and broken apart. Species have risen and gone extinct. The whole drama of Earth's history replaying 20 times over while the Sun traces its vast circle. And the galaxy itself is moving, falling toward the Andromeda Galaxy under mutual gravitational attraction. In about 4 billion years, the two galaxies will collide, though collide is perhaps the wrong word, since stars are so widely separated that actual stellar collisions will be rare. Instead, the galaxies will pass through each other, their gravitational interactions flinging stars into new orbits, triggering bursts of star formation as gas clouds collide and compress, eventually merging into a single larger galaxy. The Sun will likely survive this encounter, though it might be flung into a different orbit, perhaps farther from the galactic centre, perhaps closer. Earth might survive as well, or it might not. By then the Sun will be well into its red giant phase, and Earth's fate depends more on the Sun's evolution than on the galactic merger. But the night sky, 4 billion years from now, will be dramatically different. Andromeda no longer a distant smudge, but a vast band of light dominating half the sky, its stars mingling with the Milky Ways, the whole system in glorious chaos. You find yourself wondering what humans, or whatever humans become, will make of that sky. Will there still be observers, still beings capable of looking up and understanding what they see? 4 billion years is a long time, longer than life has existed on Earth, long enough for evolution to produce outcomes utterly unlike anything alive today. Or perhaps intelligence will have moved beyond biological substrates entirely, uploaded into machines or distributed across networks spanning star systems, no longer bound to planets or even to matter as we understand it. Or perhaps intelligence will have destroyed itself, a brief flicker in cosmic time, leaving Earth silent again, its atmosphere gradually stripped away by the aging sun, its oceans boiled off, its surface eventually sterilized and dead. There is no way to know. The future is not written in the stars, only probabilities and possibilities, the outcomes of processes too complex to predict in detail. But standing here now, under these stars, you feel a strange sense of continuity with all the other humans who have looked up and wondered. Ancient astronomers tracking the movements of planets, trying to predict eclipses and conjunctions. Medieval scholars debating the nature of the celestial spheres, whether the stars were holes in a crystalline dome or distant suns. Renaissance observers peering through the first telescopes, discovering moons around Jupiter and phases of Venus, realizing that the Earth was not the center of everything. Victorian spectroscopists analyzing starlight, discovering that the same elements present on Earth existed in the stars, that the universe was made of comprehensible matter following comprehensible laws. 20th century astronomers discovering the expansion of the universe, the cosmic microwave background, the acceleration of that expansion driven by something called dark energy that no one yet understands. And now, 21st century observers finding planets around other stars, measuring their atmospheres, searching for biosignatures, beginning the long process of determining whether life is common or rare, whether intelligence is inevitable or unlikely. Each generation builds on the work of previous generations, the accumulation of knowledge, a long collaborative project spanning centuries, millennia. No one person understands all of it. The universe is too large, too complex, the details too intricate for any single mind to hold. But collectively, the species knows more than it ever has, and that knowledge continues to grow, every new telescope revealing new puzzles, every new measurement refining our understanding or overturning old assumptions. It is a hopeful thought in a way. Despite everything, despite wars and famines and plagues, despite the petty cruelties and grand tragedies that fill human history, there has always been this thread of curiosity, this drive to understand, to look beyond the immediate and grasp at larger truths. The cold is becoming uncomfortable now, insistent. You stamp your feet, blow on your hands, knowing you should go inside but still reluctant to leave. Above, the stars continue their slow procession across the sky, rising in the east and setting in the west, the apparent motion caused by Earth's rotation, the planets spinning beneath the fixed stars. Except the stars are not fixed at all. They are all in motion, orbiting the galaxy, some moving faster and some slower, some heading toward the galactic center and some away, the whole system in constant flux. The constellations you see are temporary arrangements, patterns that happen to exist now, but will change over thousands and millions of years as the stars drift relative to each other. The Big Dipper will not always look like a dipper. Orion will not always look like a hunter. The sky is not static but evolving, and if you could watch it in fast forward over millions of years, you would see the stars sliding past each other like boats on a river, the familiar patterns dissolving and new ones forming, the sky continually remaking itself. You think about the people who will stand here in the future, 1,000 years from now, 10,000, 100,000. Will they still look up? Will they still wonder? Or will the stars have become so familiar, so mapped and catalogued and understood that they lose their power to inspire awe? You hope not. You hope that no matter how much is learned, there will always be deeper questions, mysteries that retreat as you approach them, phenomena that surprise and confound. The universe seems constructed that way, every answer revealing new questions, every solved puzzle showing 10 more waiting behind it. Quantum mechanics and general relativity, the two most successful theories in physics, are incompatible with each other, both correct within their domains but unable to be unified into a single framework. Dark matter and dark energy together make up 95% of the universe's mass energy, and no one knows what they are. The fundamental constants of physics, the speed of light, the strength of gravity, the charge of the electron, have the values they have for no known reason, and if they were even slightly different, stars could not form, chemistry could not work, life could not exist. Are those constants truly constant, Or do they vary across space and time? Are there other universes where they have different values? And if so, are those universes real in the same sense this one is? Or are they mathematical abstractions, hypotheticals that exist only in equations? These questions have no answers yet, may never have answers, but they are worth asking. They frame the boundaries of knowledge, the places where understanding fades into speculation and philosophy, and they remind you that for all humanity has learned, the universe remains fundamentally mysterious, its depths unexplored, its possibilities vast. Standing under these stars, you are standing at the edge of the known world, looking out into darkness that is not empty but full of stars too distant to see, galaxies beyond counting, structures and phenomena that do not yet have names. And somewhere in that vastness, perhaps, others are standing as you are, looking up at their own skies, wondering about the nature of things, asking the same questions in different languages, seeking the same understanding. The thought makes you feel both small and connected. Small because you are one organism on one planet, orbiting one unremarkable star in a galaxy, containing hundreds of billions of stars in a universe, containing hundreds of billions of galaxies, and connected because that very awareness, that ability to comprehend scale and distance and time, is itself remarkable, a product of 4 billion years of evolution, producing nervous systems complex enough to model the universe, to hold abstractions, to wonder about things far removed from immediate survival needs. Consciousness is rare, as far as anyone knows, possibly unique to Earth, possibly scattered across the galaxy, possibly common but never long-lasting, each instance flickering briefly before extinction. But however rare it is valuable, this capacity to know and question and care. It is what allows the universe to know itself, to examine its own structure and history, to ask why it exists and whether it means anything. You do not have answers to those questions, and you suspect no one does. But you have this moment, this experience of standing under stars on a cold night after rain, your mind full of thoughts about fusion and gravity and time, your body full of atoms forged in stars, your consciousness a brief eddy in the flow of matter and energy that constitutes the universe. It is enough. It has to be enough. The stars do not care whether you understand them, do not notice your attention, will continue burning long after you're gone. But you are here now, aware and alive, capable of appreciating them, and that seems like something worth protecting, worth preserving, worth passing on to whatever comes next. Finally, because you must, you turn away from the sky and walk toward the warmth and light of your home, but you carry the stars with you, their quiet light imprinted on your thoughts, their distant fires still burning in your mind. Tomorrow the rain might return, the clouds might cover everything again, and you will go about your day without thinking of stars at all. But they will still be there, above the weather, beyond the atmosphere, burning steadily in the dark, red dwarfs and blue giants, yellow stars and orange stars, binaries and variables, clusters and streams, all the quiet hearts of other suns, all the possibilities they hold, all the worlds they warm, all the stories they tell to anyone willing to listen. The solar system is not just 8 major planets and a few famous moons. Between and beyond them drift many smaller worlds, round but not dominant, icy or rocky, dim and slow. These are the dwarf planets, quiet bodies whose orbits and histories tell us how the system really formed. They circle in the spaces we used to think were empty, carrying within their frozen surfaces and strange orbits the memory of violence and creation, of collisions that never quite finished, of planets that never quite grew up. A dwarf planet orbits the Sun, has enough mass for its own gravity to pull it into a roughly spherical shape, but hasn't cleared its orbit of other debris. It's not a moon, but it also doesn't rule its neighbourhood the way Earth or Jupiter does. It exists in a middle category, and that middle space turns out to be more interesting than either extreme. These worlds are large enough to be round, to have internal structure, perhaps even geological activity, but small enough that they share their orbital space with thousands of siblings and cousins. They are the in-between things, the objects that make us question our definitions and force us to admit that nature doesn't care much for our neat categories. The closest dwarf planet to the Sun is Ceres, living in the asteroid belt between Mars and Jupiter. It was discovered in 1801 by Giuseppe Piazzi, who thought he'd found a missing planet predicted to exist in the conspicuous gap between the orbits of Mars and Jupiter. For a brief, glorious time, Ceres was called a planet. Then more objects were found in the same region, and Ceres was demoted to asteroid, lumped in with irregular chunks of rock. But Ceres is different. It's dark and round and relatively small, yet large enough to be more like a protoplanet than a chunk of rubble. When NASA's Dawn spacecraft arrived in 2015, it revealed a world. Ceres is a mix of rock and ice with hints of salty brines below the surface. The famous bright spots in Ocata crater, deposits of reflective salts, gleam like eyes in the darkness, suggesting past or perhaps intermittent briny activity. Water mixed with salts has seeped up from below, evaporating and leaving mineral deposits that catch sunlight like snow on a winter field. Ceres may have had a modest subsurface ocean earlier in its history, a global shell of liquid water beneath an icy crust. That ocean is now partly frozen, but it left chemical traces, geological scars, bright wounds that tell of a more active past. Here in the asteroid belt, where we expected only dead rock, there was water and salt and perhaps the faintest possibility of chemistry complex enough to surprise us. But the real dwarf planet story begins farther out, in the cold and dark beyond Neptune. Early in the 20th century, small irregularities in the orbits of Uranus and Neptune inspired searches for a hypothetical Planet X, a massive world whose gravity was tugging at the ice giants. Percival Lowell spent years looking for it, drawing maps and making calculations, convinced that a ninth planet lurked in the outer darkness. He died without finding it. In 1930, a young astronomer named Clyde Tombaugh, working at Lowell's observatory in Arizona, finally spotted a tiny distant object moving slowly against the background stars. It was named Pluto, after the Roman god of the underworld, a fitting name for something so far from the sun's light and warmth. For 76 years, Pluto was the ninth planet. School children memorized its name. It was the odd one out, smaller than Earth's moon, with a tilted and elongated orbit that sometimes brought it inside Neptune's path, but it was ours. It marked the edge of the known solar system, a frozen marble at the boundary of everything. We knew almost nothing about it. Through telescopes, Pluto was a blur, a point of light that barely moved. We measured its brightness, watched it dim when its moon passed in front of it, and guessed at what it might be. Then, slowly, our understanding changed. Pluto is small, with a diameter of about 2,300 kilometres, much less than Earth's moon, but it has a complex personality. Its composition is ice and rock mixed together, a frozen slush of nitrogen, methane and water ice over a rocky core. It has a thin nitrogen atmosphere that expands when Pluto swings closer to the Sun and collapses back to frost on the surface during the colder parts of its orbit. And it has a large moon, Charon, so similar in size that together they form something more like a binary system than a planet with a satellite. Charon is about half Pluto's diameter, massive enough that the centre of mass between them lies outside Pluto's surface. They orbit that common point, locked in a gravitational embrace, always showing each other the same face. When NASA's New Horizons spacecraft flew by Pluto in July 2015, it transformed our picture of this dwarf planet. After 9.5 years of travel, the spacecraft raced past at 50,000 kilometers per hour, cameras clicking, instruments measuring, sending back images that stunned everyone who saw them. There was the heart-shaped bright region, Tombaugh Regio, smooth and pale against darker terrain. Smooth nitrogen plains, frozen lakes of nitrogen ice lying flat in enormous impact basins with no craters at all, meaning they were young, geologically active, recently resurfaced. Towering water ice mountains rising 3.5 kilometers high, floating on a substrate of softer nitrogen ice like icebergs on a frozen sea. Signs of glacial flow, of nitrogen ice creeping downhill over millions of years, of sublimation pits and polygonal convection cells and possible cryovolcanoes. Pluto is not a static ice ball. It shows evidence of geological processes even this far from the Sun, 39 times farther from our star than Earth is. Something is heating Pluto from within, keeping it alive. Charon too surprised us. It has a reddish polar cap, probably, made of organic molecules called tholins, created when methane escaping from Pluto is broken down by ultraviolet light and drifts to Charon's poles. It has vast canyons, fractures that stretch across its surface, evidence that its interior once froze and expanded, cracking the crust. And it has a smoother southern hemisphere, suggesting past resurfacing, maybe from cryovolcanic activity or ancient subsurface water, breaching the surface and then freezing. Pluto and Charon are tidally locked to each other, always showing the same faces across their mutual orbit. They dance together, two partners in the dark, moving as one. Pluto has 4 smaller moons as well: Nix, Hydra, Kerberos, and Styx, discovered through careful observation and named for figures associated with the underworld. These tiny moons tumble and spin in complex ways, their orbits influenced by the gravitational tug-of-war between Pluto and Charon. They're irregular, potato-shaped, probably fragments from some ancient collision. This little system resembles a miniature version of planet-moon dynamics, scaled down and colder and stranger. Pluto is not alone out there. It's one of many icy bodies in the Kuiper Belt, a donut-shaped region beyond Neptune containing countless small objects, leftovers from the solar system's formation. The Kuiper Belt is named for Gerard Kuiper, who predicted its existence, though others had similar ideas earlier. It's a distant reservoir of comets and ice dwarfs, stretching from Neptune's orbit at 30 astronomical units out to perhaps 50 or more. Many Kuiper Belt objects follow resonant orbits with Neptune. Some, like Pluto, are in a 3-to-2 resonance, orbiting the Sun twice for every 3 Neptune orbits. This resonance protects them from close encounters with Neptune, locking them into stable patterns that have persisted for billions of years. Pluto is a standout among many cousins, the first one we found, the one we knew longest, but just one of a population. In the early 2000s, astronomers began finding more objects out there, large enough to be round, similar in size to Pluto. One of them, discovered in 2005, was nicknamed Xena, before being officially named Eris. Eris is similar in size to Pluto and more massive, with a distant elongated orbit that takes it out to 96 astronomical units at its farthest point. Its discovery raised a question that couldn't be ignored. If Pluto is a planet, what about Eris? And what about other similar objects that were sure to be found? The solar system suddenly seemed crowded with potential planets. Were we going to have dozens of planets? Hundreds? The International Astronomical Union gathered in Prague in 2006 to settle the matter. After days of debate, they refined the definition of a planet. A planet orbits the Sun, has enough mass to be roughly spherical, and has cleared its orbit of other debris. That last criterion was the key. Jupiter and Earth have cleared their orbits. There are no comparable objects sharing their paths. Pluto has not. The Kuiper Belt is full of objects in similar orbits. Rather than expanding the list of planets to dozens, astronomers created the dwarf planet category. Pluto, Eris and Ceres became members, later joined by other candidates. Pluto did not shrink. Its size, its moons, its mountains and glaciers remained the same. Its label simply changed to reflect its neighbourhood. Some people were upset. Pluto had been a planet for most of living memory, and now it was something else. But the reclassification wasn't a demotion. It was a recognition that the solar system is more diverse than we'd thought, that there are categories between planet and asteroid, and that Pluto is the king of a vast population of distant frozen worlds. Other dwarf planets joined the list. Haumea, discovered around the same time as Eris, is one of the strangest. It spins incredibly fast, completing a rotation in under 4 hours, and that rapid spin stretches it into an elongated shape, almost like a rugby ball or a squashed egg. It's about 2,000 kilometres along its longest axis, but only half that in the other directions. Its surface is bright, coated in water ice that reflects most of the light that hits it, making Haumea one of the most reflective objects in the solar system. It has 2 small moons, Hi'iaka and Namaka, named for Hawaiian goddesses, and a ring, the first ring system discovered around a dwarf planet. The ring is narrow and lies in Haumea's equatorial plane, probably formed from debris kicked up by an ancient collision. Haumea shows how spin, collisions, and composition can produce unusual shapes at the edge of the system, how even small worlds can be complex and surprising. Makemake, another distant dwarf planet, has a reddish surface, likely coated in methane and other volatile ices. It's smaller than Pluto, about 1,400 kilometres in diameter, with a thin or transient atmosphere, if any. Observations suggest dark patches and bright regions, varied terrain shaped by sunlight, sublimation, and perhaps seasonal frosts. Makemake is named after a creator deity in Rapa Nui mythology, continuing the tradition of linking these distant objects to human stories and cultures. It orbits far from the Sun, taking more than 300 years to complete one orbit, moving slowly through the dark like a forgotten memory. Several dwarf planets may hold subsurface oceans or layers of soft, partially melted ice. Internal heating from radioactive decay and tidal flexing can keep layers of water or ammonia-water mixtures from freezing completely solid. On such small worlds, the ice shell and any ocean beneath are thick compared to the overall size. Ceres may have had one. Pluto might still have one. A thin layer of liquid water or ammonia brine between the ice crust and rocky core, kept from freezing by radiogenic heat and the slow decay of internal warmth. These are not warm oceans. They're cold, salty, under immense pressure in total darkness. But they're liquid, and where there's liquid water there's the faintest possibility of chemistry, of molecules meeting and reacting in ways we don't yet understand. Some dwarf planets have moons and even rings, suggesting past collisions and complex histories. Fragments from impacts can form satellites. Debris can spread into rings. Each system, Pluto and Charon, Eris and its moon Dysnomia, Haumea with its moons and ring, is a small family, evidence that even tiny worlds can host miniature systems. These moons are capture victims or collision fragments, born in violence and now locked into orbits that will last until the sun dies. Their surfaces are scarred with craters, their interiors long since frozen solid, but they endure, circling their primaries in the cold. The orbits of dwarf planets are often tilted relative to the main planetary plane, and quite elongated, carrying them from relatively closer in to far out. Pluto's orbit is inclined 17 degrees to the ecliptic and eccentric enough that sometimes it's closer to the Sun than Neptune. Eris's orbit is even more extreme, tilted 44 degrees and stretching from 38 to 96 astronomical units. These paths hint at past gravitational encounters with giant planets or migration processes in the early solar system. When Neptune migrated outward, billions of years ago, it scattered many Kuiper belt objects into tilted, elongated orbits. The outer regions are not tidy. They're the record of dynamic reshaping, of chaos, and near collisions and bodies flung into orbits that will never repeat in any human lifetime. Ceres lives in the asteroid belt where rock dominates and Jupiter's gravity stirs orbits. Pluto, Eris, Haumea and Makemake orbit in the icy Kuiper belt. Both environments reveal different aspects of planetary formation. Ceres is a leftover building block of inner planets, a protoplanet that never finished growing because Jupiter's gravity prevented the asteroid belt from coalescing. Outer dwarf planets are pieces of the distant disk, objects that formed in the cold and stayed there, never swept up into the ice giants or ejected from the system entirely. They're survivors, fossils from the era when the solar system was assembling itself. Dwarf planets fit into models of planet formation in important ways. In many simulations, small bodies merge to form larger planets, but some are left behind, never fully accreted or later scattered outward. Dwarf planets are surviving protoplanets and large planetesimals, frozen embryos that never became adults. They tell us what the early solar system looked like, when the sun was young and the disk was full of ice and rock, when planets were still growing and the orbits were unstable. They're witnesses to a time we can't see directly, carrying evidence in their compositions and orbits, in the craters on their surfaces and the frozen oceans beneath. We study these distant objects using telescopic imaging, measurements of brightness and colour, stellar occultations where a dwarf planet passes in front of a star, and spacecraft flybys like Dawn and New Horizons. Each technique adds bits of information about size, shape, atmosphere and surface composition. Telescopes can detect colour variations that hint at surface materials. Occultations let us measure size and detect thin atmospheres. Spacecraft give us close-up images, spectra, gravity measurements, the kind of detail that transforms a point of light into a world. But spacecraft are rare and expensive, and the journey takes years or decades. Most dwarf planets we know only from a distance, from faint signals gathered by patient observers. The names chosen for these worlds link modern scientific classification to older human stories and cultures. Ceres from Roman agriculture, goddess of grain and harvest. Pluto from the underworld, the shadowy realm beyond life. Eris from discord and strife. Haumea from Hawaiian mythology, goddess of childbirth. Make from Rapa Nui tradition, creator of humanity. Names give these distant objects a place in our language as well as our equations, connecting them to the myths and stories humans have told for thousands of years. Even now, when we name something, we're telling a story about it, placing it in relation to ourselves and our history. There are likely more dwarf planets we haven't officially recognised yet, large Kuiper belt objects and distant bodies that meet the criteria but await detailed study. As surveys improve, the catalogue of dwarf planets will probably grow. There are candidates out there: Sedna, Quaoar, Orcus, Gongong, dozens more, some with moons, some with unusual orbits, all waiting for enough data to be confirmed. The solar system will feel more populated in its outer parts, more crowded with spherical worlds that aren't quite planets, but aren't quite asteroids either. The dwarf planet concept forces us to refine our language. Instead of a simple planet-not-planet divide, we now see a spectrum: small irregular bodies, dwarf planets, terrestrial planets, gas giants, ice giants. Our mental picture becomes less like a simple list and more like a gradient of sizes and roles. Size matters, but so does location, composition, and dynamical history. A world is defined not just by its mass, but by its context, by where it lives and what it's made of and how it interacts with its neighbours. This is messier than a clean taxonomy, but it's more honest, more reflective of how nature actually works. Other star systems likely have their own dwarf planets and belts. If our solar system has many minor planets, other stars probably do as well. Somewhere else, small icy worlds may orbit in the cold, their surfaces slowly changing under faint suns, unnoticed except by careful observers. We're beginning to detect debris disks around other stars, belts of dust and ice that might hide populations of dwarf planets. We won't see them directly for a long time, they're too small and dim, but we can infer their presence, imagine them circling distant suns in patterns we're only beginning to understand. Dwarf planets, though small and remote, help answer big questions: where water and volatiles reside, how planets grow, and how dynamic the outer solar system has been. They expand our understanding of what counts as a world. A world doesn't have to be large or close or well lit. It can be small and far and dark and still be complex, still have mountains and glaciers and maybe oceans, still have a story worth telling. These distant spheres circle in the cold, carrying evidence of the solar system's formation, of collisions and migrations and the slow sculpting of orbits by gravity. They're quiet, overlooked, easy to dismiss, but they matter. They tell us that the solar system is bigger and stranger than we thought, that the edges are not empty but full of life, not biological life, but geological life, the slow breath of worlds that change and endure and remember. Seen from far away, the solar system is bright inner planets near the sun, giant planets farther out, and beyond, dim little spheres tracing slow, tilted loops through the dark. Under the hush of rain, these distant dwarf planets circle on timescales much longer than a human life, quietly continuing the story of how our solar system came to be. They're the forgotten ones, the overlooked ones, the worlds that didn't make it into the simple diagrams we draw for children. But they're real, and they're out there, and they're waiting for us to notice them, to send our eyes and instruments their way, to learn what they have to teach. In the end, they remind us that nature is not obligated to fit our categories, that the universe is full of in-between things, and that sometimes the most interesting stories are told by the smallest voices. They drift in the darkness where sunlight is barely more than starlight, where a year lasts centuries, and the temperature never rises above a few dozen degrees above absolute zero. These are the patience worlds, the waiting worlds, places where change happens so slowly that a human lifetime would capture only the smallest fraction of a season. Ice sublimates molecule by molecule. Craters accumulate over millions of years. The faint tug of distant Neptune shifts orbits by fractions of degrees across geological epochs. Time moves differently out there, stretched and slowed like light redshifting as it climbs out of a gravity well. When we think about planets, we think about worlds we could stand on, worlds with horizons and weather and maybe even life. But dwarf planets challenge that image. Most of them are places where standing would mean sinking into nitrogen frost or methane snow, where the horizon curves away sharply because the world is so small, where the sun hangs in a black sky as just another bright star among many. They're alien in a way that even Mars isn't, because Mars at least feels like a place humans might eventually walk. Dwarf planets feel like monuments to time and cold, sculptures carved by forces so gradual they're almost invisible. Consider what it means that Pluto has glaciers. On Earth, glaciers flow because ice under pressure becomes plastic, because the weight of snow accumulated over centuries presses down and forces the ice beneath to deform and flow downhill. Pluto's nitrogen ice does the same thing, but slower, colder, under gravity that's barely 6% of Earth's. The ice in Sputnik Planitia flows at rates of centimetres per year, creeping across the landscape like cold honey, filling in craters, smoothing away the scars of ancient impacts. This is geology at the edge of possibility, processes happening so slowly that even geologists have to think in units of millions of years to see the patterns. And yet these worlds are not dead. Dead implies they were once alive and ceased to be. These worlds are something else, dormant perhaps, or simply operating on timescales we struggle to comprehend. Ceres has had recent cryovolcanic activity within the last few million years, possibly within the last few thousand. Ahuna Mons, a mountain on Ceres that rises 4 kilometres high, is probably a cryovolcano, a place where salty water mixed with mud erupted from below and froze into a dome. The Dawn spacecraft found organic molecules on Ceres' surface, complex carbon compounds that might have formed in the subsurface ocean and been brought up by geological activity. These are not the building blocks of life, not quite, but they're the chemistry that comes before, the ingredients waiting for the right conditions. Pluto's surface is young in places, which means something is still happening there. The nitrogen plains of Sputnik Planitia have almost no craters, suggesting they've been resurfaced within the last 10 million years, maybe within the last million. That's yesterday in geological terms. Something is driving this activity. The most likely explanation involves a subsurface ocean of water mixed with ammonia, kept liquid by radiogenic heat from the decay of radioactive elements in Pluto's core. The ocean might be in contact with the rocky core, allowing chemical reactions between water and rock, the kind of reactions that on Earth support hydrothermal vent ecosystems. No one is suggesting there's life in Pluto's ocean. The conditions are too cold, too hostile, too far from any energy source, but the chemistry is there, the possibility space exists. The same might be true for other dwarf planets. Eris is large enough that it should have retained heat, should have a differentiated interior with a rocky core and icy mantle. If it has enough ammonia or other antifreeze compounds mixed with its water ice, it could have a subsurface ocean. We don't know. We've never sent a spacecraft there, never gotten close enough to measure its gravity field or look for signs of geological activity. Eris remains, mostly a mystery, a bright dot in telescopes, a world we know exists but haven't truly met. The same is true for most of the other candidates. Sedna, discovered in 2003, has one of the most extreme orbits known, stretching from 76 astronomical units at its closest to nearly 1,000 at its farthest. It takes more than 11,000 years to complete one orbit. Right now it's approaching perihelion, the closest point to the Sun, but even at its closest it's more than twice as far out as Neptune. Its orbit is so extreme that it's hard to explain. Neptune's gravity can't reach it. Some other force must have pulled Sedna into that orbit. Maybe a rogue planet that was ejected from the solar system early on. Maybe a passing star, maybe even the gravitational influence of the galaxy itself. Sedna is evidence of something we don't fully understand, a fossil orbit that points to events billions of years ago. Then there's Gong, another distant object with a large moon, about 1,200 kilometres across, red-tinted, probably rich in methane ice. There's Quaoar, which has a ring that shouldn't exist according to our models, because it lies too far from the dwarf planet for the ring particles to be stable. The ring should either spread out or coalesce into a moon, but it persists, challenging our understanding of orbital dynamics. There's Orcus, sometimes called the anti-Pluto because it has an orbit similar to Pluto's but phase-shifted, so when Pluto's at perihelion, Orcus is at aphelion, and vice versa. These objects are more than just catalogue entries. Each one is a puzzle piece, a clue to how the solar system formed and evolved. The formation story of dwarf planets is intertwined with the formation of everything else. In the earliest days, 4.5 billion years ago, the solar system was a disk of gas and dust surrounding a newborn star. In the cold outer regions of that disk, beyond what would become the orbits of Jupiter and Saturn, ice could condense. Water ice, methane ice, ammonia ice, carbon dioxide ice, all the volatiles that would have stayed gaseous closer to the Sun. Tiny ice grains stuck together, building up into larger and larger chunks. Some of these chunks grew into the cores of Uranus and Neptune. Others grew into large planetesimals, protoplanets that might have eventually become planets if given enough time and material, but they didn't get that time. The giant planets formed and began migrating. Jupiter moved inward, then outward. Saturn moved outward. Uranus and Neptune scattered outward, ploughing through the outer disk like icebreakers through a frozen sea. They flung countless objects into chaotic orbits. Many were ejected from the solar system entirely, sent out into interstellar space. Others were thrown into the inner solar system, bombarding the terrestrial planets in what we call the late heavy bombardment. Still others were perturbed into orbits that kept them in the outer solar system, but prevented them from ever accreting into larger bodies. These survivors are the dwarf planets and Kuiper belt objects we see today. The asteroid belt tells a similar story on a smaller scale. Between Mars and Jupiter, rocky planetesimals were accumulating, building up into larger bodies. Ceres was one of the largest, well on its way to becoming a proper planet. But Jupiter's gravity stirred the region, increasing collision velocities until impacts shattered bodies instead of merging them. Ceres survived because it was already large enough to be mostly immune to catastrophic disruption, but it never grew larger. The material that should have formed a planet between Mars and Jupiter is now spread across millions of asteroids, with Ceres as the lone dwarf planet, a reminder of what might have been. This history is written in the compositions and orbits of dwarf planets. The inner solar system is rocky because the sun's heat drove off volatiles. The outer solar system is icy because the cold allowed them to condense. Ceres, straddling the boundary, is a mix, rock and ice in roughly equal proportions, a transitional object that captures the gradient from hot to cold. Pluto and the other Kuiper belt dwarfs are mostly ice with rocky cores, built from material that condensed in the cold beyond Neptune. Their surfaces are coated with volatile ices, nitrogen, methane, carbon monoxide, that would evaporate instantly in the inner solar system but remain frozen in the outer dark. The colours of these worlds tell us what they're made of. Reddish surfaces suggest organic compounds, complex carbon molecules called tholins that form when simpler molecules like methane are broken apart by ultraviolet light or cosmic rays, and then recombine into larger structures. These tholins are similar to the haze that shrouds Saturn's moon Titan, the organic gunk that coats many outer solar system objects. Bright, reflective surfaces suggest fresh ice, perhaps water ice on Haumea or nitrogen ice on Pluto, surfaces that haven't been space-weathered and darkened by eons of radiation exposure. Dark surfaces mean old ice, ice that's been sitting in the sun's faint light for billions of years, accumulating a layer of irradiated, darkened material. Spectroscopy lets us identify these materials even from great distances. When sunlight reflects off a dwarf planet, certain wavelengths are absorbed by molecules on the surface, leaving dark lines or bands in the spectrum. Water ice absorbs strongly in the infrared. Methane has distinctive absorption bands. Carbon monoxide, nitrogen, ammonia, each has its own spectral signature. By carefully measuring the light that reaches us, astronomers can determine what these distant surfaces are made of without ever sending a probe. It's like tasting a dish and identifying the ingredients by flavour alone, except we're tasting light that's travelled billions of kilometres through space. The presence of moons around dwarf planets tells us about their collision histories. Charon is too large to have formed from an impact on Pluto. It probably formed from a glancing collision between two large protoplanets, an impact that sent debris into orbit that then coalesced into Charon. The smaller moons, Nix, Hydra, Kerberos, Styx, are probably fragments from that same collision or from later impacts. Dysnomia, Eris's moon, likely formed from an impact. Haumea's moons and ring almost certainly did, because Haumea itself shows signs of a massive collision that set it spinning and left it with a bright icy surface, where deeper material was excavated and exposed. These collisions were violent beyond imagination. When two dwarf planet-sized objects collide at speeds of several kilometres per second, the energy released is measured in billions of nuclear bombs. Material is vaporized, melted, shattered, thrown into space. Some of it escapes entirely. Some falls back to form a debris disk. Some coalesces into moons. The primary bodies are deformed, heated, sometimes partially melted despite the cold. These are events that reshape worlds, that turn spheres into oblongs, that create families of objects where there was once just one, and yet these worlds survive. They're battered, scarred, but intact. The craters that cover their surfaces are records of impacts large and small, accumulated over billions of years. Each crater is a timestamp, a moment when a chunk of rock or ice travelling through space happened to intersect this particular world's orbit. The largest craters are ancient, filled in by later geological activity or degraded by slow sublimation. The smallest are fresh, crisp, their rims sharp and bright. By counting craters and measuring their sizes, planetary scientists can estimate surface ages, can figure out which regions are old and which are young, which have been resurfaced and which have remained unchanged since the solar system's youth. Pluto's heart, Tombaugh Regio, is almost crater-free, which means it's young. The nitrogen ice there is flowing, resurfacing the region, erasing impacts. But just outside the heart, the darker regions called Cthulhu Regio and Mengpo, the surface is ancient, covered in craters, probably dating back billions of years. The contrast is stark, smooth plains next to rugged ancient terrain. This tells us that Pluto's geological activity is localized, that not all of the dwarf planet is active, only certain regions where conditions allow ice to flow, or where internal heat reaches the surface. Charon shows a similar dichotomy. Its northern hemisphere is fractured and rough, while its southern hemisphere is smoother, less cratered, suggesting it was resurfaced at some point in the past. The dividing line between the two hemispheres is sharp, a geological boundary that marks some change in Charon's history. Perhaps the subsurface ocean froze and expanded, cracking the northern hemisphere while the south was covered by cryovolcanic flows. Perhaps tidal heating, from Pluto, back when Charon's orbit was still evolving, was stronger in one hemisphere than the other. We don't know for certain. We have one flyby's worth of data, a handful of images and measurements, and from that we're trying to reconstruct billions of years of history. This is the nature of planetary science in the outer solar system. We work with fragments, with glimpses, with data so sparse that every pixel and every spectrum is precious. When New Horizons flew past Pluto, it took thousands of images, but even so, it only photographed about half the surface at high resolution. The other half remains mostly unmapped, known only from lower resolution images taken from farther away. For most other dwarf planets, we have even less. We have light curves showing how their brightness changes as they rotate, suggesting shapes and surface patterns. We have colours indicating compositions. We have occultation data giving sizes and hints of atmospheres. But we don't have maps. Not really. We have sketches, outlines, suggestions of what these worlds might be like. And yet from these sketches we build understanding. We compare Pluto to other icy moons like Triton and Europa and Enceladus, looking for common patterns. We compare Ceres to asteroids and comets, trying to understand where it fits in the spectrum of small bodies. We run computer simulations of planetary migration and see if they produce populations of dwarf planets with orbits like the ones we observe. We model interior structures, figuring out how much rock and ice would be needed to produce the observed mass and size, whether a subsurface ocean is plausible, how much heat would be generated by radioactive decay. Slowly, piece by piece, we're building a picture of these distant worlds. The search for more dwarf planets continues. Modern surveys like the Dark Energy Survey, the Panoramic Survey Telescope and Rapid Response System, and the upcoming Vera Rubin Observatory are scanning the sky, looking for faint moving objects. Most of what they find are smaller, Kuiper Belt objects a few hundred kilometres across, trans-Neptunian objects in distant orbits. But occasionally something larger appears, something big enough to be round, to be a dwarf planet. Each discovery adds to our catalogue, refines our understanding of the outer solar system's population. There are predictions of even larger objects out there. Some astronomers have proposed the existence of Planet 9, a hypothetical super-Earth or mini-Neptune in a distant, elongated orbit, based on clustering patterns in the orbits of extreme trans-Neptunian objects. If Planet 9 exists, it would be a true planet, not a dwarf, massive enough to have cleared its orbit. But it hasn't been found yet, and the evidence is still debated. Other astronomers suggest that the clustering could be explained by observational bias, or by the combined gravitational effects of many smaller objects rather than one large one. The search continues. Whether or not Planet 9 exists, we know there are more dwarf planets waiting to be discovered. The outer solar system is vast, and our surveys have only scratched the surface. Objects in the scattered disk, the region beyond the Kuiper belt where orbits are highly elongated and randomly oriented, are particularly hard to find because they spend most of their time far from the Sun, too faint to detect. We only see them when they happen to be near perihelion, passing through the region where our telescopes can spot them. Sedna is an example. We found it during its current approach to the Sun, but in a few thousand years it will be too far away to see, vanishing into the darkness for another 11 millennia. There's also the Oort cloud, a hypothetical spherical shell of icy bodies surrounding the solar system at distances of thousands to hundreds of thousands of astronomical units. The Oort cloud has never been directly observed. It's too far away, its object's too faint, but we infer its existence from the long-period comets that occasionally fall into the inner solar system, with orbits that suggest they came from very far away. Could there be dwarf planets in the Oort cloud? Almost certainly, but we'll never see them with current technology. They're too distant, too dark, lost in the vast space between our Sun and the nearest stars. This realization that the solar system extends far beyond what we can see is humbling. We think of the solar system as our neighbourhood, as familiar territory, but most of it is terra incognita, unexplored and perhaps unexplorable. The 8 major planets and their moons, the asteroids and comets we've visited, even the dwarf planets we know about, they're all in the inner regions, the suburbs of the Sun's gravitational domain. The true edge of the solar system, the boundary where the Sun's gravity finally yields to the collective pull of the galaxy, is 1,000 times farther out than Neptune, in a region we've barely begun to map. And yet, even in what we have explored, mysteries remain. Why does Haumea spin so fast? The most likely explanation is a massive impact, but the details are unclear. Why does Makemake have such a variable surface, with bright and dark regions? Why are some Kuiper belt objects binary, 2 similar-sized objects orbiting each other, while others have tiny moons, or no moons at all? Why are the orbits of trans-Neptunian objects distributed the way they are, with certain resonances overpopulated and others nearly empty? These questions drive the science forward. Every mystery is an opportunity, every unexplained observation a clue to something we don't yet understand. Dwarf planets are windows into the solar system's past, into the era of planet formation, into the migration of giant planets and the sculpting of the Kuiper belt. They're also windows into planetary processes in extreme conditions, geology at low temperatures, atmospheres at low pressures, oceans under ice shells on worlds, barely larger than earthly moons. The future of dwarf planet exploration is uncertain. Spacecraft missions are expensive and take decades. New Horizons has already visited Pluto and the Kuiper belt object Arakoth and is now heading into interstellar space, its mission essentially complete. Dawn visited Ceres and has ended its mission, now in a permanent orbit around the dwarf planet. There are no firm plans for missions to Eris, Haumea, Makemake, or any of the other candidates. The distances are too great, the travel time's too long, the budget's too constrained. But that may change. As technology improves, as propulsion systems become more efficient, as interest in the outer solar system grows, missions may become feasible. A flyby of Eris would take less time than New Horizons took to reach Pluto if we launched at the right time, when Eris is near perihelion. An orbiter around Haumea could study its ring and moons, measure its gravity field, map its elongated shape. A lander on Makemake could sample its surface ices, search for organic molecules, measure its thin atmosphere if it has one. These are dreams for now, but not impossible dreams. In the meantime, we watch from afar, gathering what data we can, building models, making predictions, waiting for the next discovery. The dwarf planets circle in their distant orbits, patient and unchanging on human timescales, carrying their secrets through the dark. They've been there for billions of years. They'll be there for billions more, long after we're gone, continuing their slow dance around the sun. The next story is about to begin. Please relax and enjoy. The rain streaks the window pane in uneven rivers, pooling at the corners where the glass meets the frame. Outside, the sky hangs low and grey, a ceiling of cloud that seems close enough to touch. A jet passes somewhere overhead. You hear it before you see it, a distant drone that fades into the weather. Then another, higher perhaps, leaving a contrail that dissolves almost immediately in the moisture-heavy air. You don't think much about what's above the clouds. Why would you? The sky looks empty, just weather and the occasional plane. But above that blanket of grey, where the air thins and the pressure drops to nearly nothing, there's an entire layer of activity. Machines move through the vacuum in precise repeating paths, silent because there's no air to carry sound. They don't announce themselves. They don't flash lights or send down signals you can hear. They simply pass overhead, over and over, tracing invisible lines across the planet. Some are no bigger than a washing machine, others span the length of a school bus, solar panels extended like wings. They orbit in darkness and sunlight, cycling between the two every 90 minutes or so, depending on their altitude. From the ground, you'd never know they were there unless you looked for them, and even then, you'd only catch the occasional glint of reflected sunlight. A moving star that doesn't twinkle. The sky isn't empty, it's organised. Low Earth orbit sits between about 160 and 2,000 kilometres up, a band where satellites circle the planet every 90 minutes to 2 hours. Higher still, medium Earth orbit stretches from 2,000 to 35,000 kilometres, where navigation satellites spend their days, and at exactly 35,786 kilometres above the equator, there's geostationary orbit, a ring where satellites move at the same speed the Earth rotates, appearing to hover over a single spot. These aren't random placements, they're parking spots and lanes, each chosen for specific reasons: coverage, speed, persistence. Gravity and velocity lock satellites into paths that repeat, day after day like clockwork. The sky has become a layered network, each altitude serving a different purpose, each orbit a careful balance between falling and flying. Consider GPS. You use it without thinking. Pull out your phone, open a map, and a blue dot appears showing exactly where you are. It feels like magic, or at least like something simple. But there's no map in the sky. What's up there is time. 24 satellites orbit at about 20,000 kilometres, each carrying atomic clocks so precise they lose less than a nanosecond per day. These clocks tick in perfect synchronization, and each satellite broadcasts a timestamp, essentially saying, "It is now this exact moment, and I am here." Your phone's GPS receiver listens to these broadcasts from 4 or more satellites at once. The signals travel at the speed of light, but space is vast enough that tiny differences in arrival time become measurable. One satellite's signal reaches you a fraction of a millisecond before another's. From that delay, the receiver calculates distance. If you're 700 kilometers from one satellite and 800 from another, your position can only be in certain places. Add a third and fourth satellite, and the possible locations narrow to a single point on Earth's surface. It's not maps in the sky, it's synchronized clocks becoming maps through geometry and time. Other systems do the same. Russia's GLONASS, Europe's Galileo, China's Beidou, each with their own constellations overlapping in coverage. A modern phone listens to all of them, combining dozens of timing signals to pinpoint your location within meters, sometimes centimeters. The system is so reliable you forget it's there, forget that it depends on machines overhead silently counting nanoseconds. Weather satellites operate differently. Some sit in polar orbits, passing over the North and South Poles every orbit while the Earth rotates beneath them. Over days, they scan every part of the globe, building up images strip by strip. Others hover in geostationary orbit fixed above the equator, watching the same hemisphere continuously. These satellites carry cameras and sensors that see far beyond visible light. Infrared to measure temperatures, microwave bands to peer through clouds, ultraviolet channels to track ozone. They watch storms form over warm oceans, hurricanes spiral toward coasts, jet streams snake across continents. They measure humidity, wind speed inferred from cloud motion, sea surface temperatures that influence weather weeks ahead. The data streams down to ground stations where computers digest it, feeding forecast models that predict rain, heat, cold, snow. The weather app on your phone pulling up a 7-day forecast depends on satellites patiently watching from 22,000 miles away, recording subtle shifts in cloud patterns and atmospheric moisture, sending that information down to be processed into predictions. Without them, forecasters would have far fewer data points, especially over oceans and remote areas where ground stations are sparse. Communication satellites handle a different kind of traffic. Picture a large antenna pointed at a satellite in geostationary orbit transmitting a signal. The satellite's transponder receives it, amplifies it, shifts its frequency, and beams it back down to another ground station hundreds or thousands of kilometers away. The signal bends through space rather than travelling along cables or overland lines. Television broadcasts once depended heavily on this, your local cable company receiving feeds from satellites, distributing them through neighbourhood lines. Remote regions still rely on satellite phones and internet terminals because laying cables across deserts or oceans is impractical. The satellite becomes a relay tower in the sky, connecting places that would otherwise be isolated. Farther out, beyond Earth orbit, a few specialised satellites talk to probes exploring the solar system. When a spacecraft at Mars or beyond the orbit of Pluto sends data home, it's often routed through relay satellites that can capture weak signals and forward them to Earth. These deep space relays are patient listeners. They're large dishes aimed at distant machines, waiting for scheduled transmissions that take minutes or hours to arrive at light speed. Recently, the architecture has shifted. Instead of a few large, expensive satellites in high orbits, companies are launching thousands of small ones into low Earth orbit, creating constellations that blanket the planet. Starlink is the most visible example, satellites orbiting at about 550 kilometers, moving fast enough that they cross the sky in minutes. A user on the ground with a phased array antenna connects to whichever satellite is overhead at the moment, and as that satellite sets below the horizon, the connection hands off to the next one rising. The system mimics cellular towers, except the towers are moving and there are thousands of them. The benefit is global coverage. Remote islands, ships at sea, rural areas far from fibre lines, all can access broadband internet. The trade-off is that the sky now has far more moving points of light. On clear nights, especially just after sunset or before dawn when the satellites are still in sunlight, but the ground is dark, you can see them, a parade of steady lights moving in formation, bright enough to catch the eye. Astronomers have raised concerns. Long-exposure photographs meant to capture faint galaxies now include streaks from satellites passing through the frame. There are discussions about darker coatings, lower orbits that decay faster, adjusting flight paths. But the fact remains that low Earth orbit is now crowded in a way it wasn't a decade ago. These satellites communicate using radio waves and increasingly lasers. Radio has been the standard for decades. It spreads in a wide beam, tolerates clouds and rain, and doesn't require perfect aiming. Ground stations and satellites exchange signals in various frequency bands, carefully managed to avoid interference. Higher frequencies carry more data but require clearer paths. Lower frequencies penetrate obstacles better but carry less information. Engineers balance these factors based on mission needs. Recently, laser links have emerged as an alternative. A laser is a narrow beam, far more focused than radio, allowing satellites to talk to each other across thousands of kilometers with high data rates. The challenge is precision. The beam must be aimed within microradians, and anything blocking the path, clouds, particles, can disrupt the signal. Between satellites in orbit, though, the path is clear, and laser crosslinks can form meshes where data hops from one satellite to another, reducing reliance on ground stations. The sky becomes not just a collection of relays, but a network where machines talk among themselves, routing information through the constellation before sending it down. Each satellite's orbit determines what it sees. A polar orbit, inclined near 90 degrees to the equator, passes over both poles each circuit. As Earth rotates beneath, the satellite eventually covers every latitude, making polar orbits ideal for mapping and surveillance. Equatorial orbits, inclined near 0 degrees, stay close to the equator, seeing only the tropics. Inclined orbits split the difference, covering mid-latitudes effectively, but leaving polar regions largely unseen. Altitude matters too. Lower orbits offer closer, sharper views but move fast and require more satellites for continuous coverage. Higher orbits see more of the planet at once but with less detail. Geostationary orbit trades motion for persistence. The satellite appears stationary, so ground antennas can point at one spot indefinitely, but the altitude limits the sharpness of images and introduces signal delay. Designers choose paths to match missions. GPS needs medium orbits for wide coverage and predictable timing. Weather satellites benefit from geostationary positions for constant monitoring. Earth observation satellites often prefer low polar orbits for high resolution and global reach. The sky has become a patchwork of trajectories, each tuned to a specific task. And then there's the debris. Not every object overhead is functional. Defunct satellites, spent rocket stages, fragments from collisions and anti-satellite tests all remain in orbit, each following its own path governed by gravity. A broken satellite doesn't fall immediately. Depending on altitude, it might orbit for years or decades before atmospheric drag finally pulls it down. Collisions are rare but catastrophic when they happen. In 2009, an inactive Russian satellite collided with an American communications satellite, creating thousands of trackable fragments and countless smaller ones. Each piece became a new object with its own trajectory, adding to the catalogue of hazards. Ground-based radar and optical telescopes track these objects, compiling databases of known debris. Operators monitor predictions of close approaches, conjunction events, where two objects might pass within a dangerous distance. If the risk is high enough, satellites maneuver, firing thrusters to adjust their orbits slightly, buying a few extra kilometers of clearance. It's a constant process, managing a growing population of space junk that clutters the orbital lanes. Some companies are developing ways to remove debris, nets, harpoons, robotic arms, but these remain experimental. For now, the strategy is avoidance and careful tracking, treating the sky like a highway with obstacles to navigate. On the ground, networks of sensors watch all this. Radar stations pulse energy skyward, detecting objects by their reflections. Optical telescopes photograph the sky repeatedly, comparing images to identify moving points of light. Computers process the observations, calculating orbits and predicting future positions. This is called space situational awareness, a kind of air traffic control for orbits. Without it, launching new satellites would be risky. You wouldn't know if you were placing a satellite into a path already occupied by debris. Agencies share catalogues, though not always completely. Some objects, particularly military satellites, are tracked but not publicly listed. The goal is to keep the sky usable, to prevent cascading collisions that could render certain orbits too dangerous for operations. It's infrastructure maintenance for an environment most people never think about, a background effort to keep the lanes clear. Sometimes the space environment makes itself visible. Auroras, northern and southern lights, occur when charged particles from the sun follow Earth's magnetic field lines down into the atmosphere, typically near the poles. These particles, part of the solar wind, stream constantly from the sun, but during solar storms the flow intensifies. When they collide with oxygen and nitrogen atoms high in the atmosphere, energy transfers and atoms emit light. Greens, reds, purples, shimmering curtains that ripple across the night sky. For people on the ground, it's beautiful, something to photograph and marvel at. For satellite operators, it's a concern. The same energetic particles that create auroras can disrupt radio communications, interfere with GPS signals, and even damage electronics on satellites if radiation levels spike high enough. Solar storms can also heat and expand the upper atmosphere, increasing drag on low-orbit satellites, pulling them lower faster than planned. Operators monitor space weather forecasts, watching for coronal mass ejections and solar flares, adjusting satellite operations when necessary. The auroras are feedback, a visible sign of the invisible interaction between the sun, Earth's magnetic field, and the machines we've placed in between. Getting satellites into orbit requires rockets. Launch is a controlled explosion, burning tons of fuel to lift a payload out of the atmosphere and accelerate it to orbital velocity, roughly 7 to 8 kilometers per second for low Earth orbit. Rockets climb vertically at first, then gradually pitch over, building horizontal speed as they rise. The first stage burns out and falls away. Upper stages continue, fine-tuning the trajectory. Once the desired altitude and velocity are reached, the payload separates and deploys. Some satellites have their own propulsion to adjust their orbit further, moving from a transfer orbit to a final operational orbit. After deployment, small thrusters handle station keeping, minor adjustments to counteract atmospheric drag, correct drift, or avoid debris. Fuel is precious. Satellites carry only so much, and once it's gone, they can't maneuver anymore. Operators budget fuel carefully, planning years of small corrections, knowing that eventually the satellite will become uncontrollable and either be moved to a graveyard orbit or left to decay. The launch is a one-time event, but maintaining the orbit is ongoing. Geostationary orbit deserves special attention. At exactly 35,786 kilometers above the equator, a satellite's orbital period matches Earth's rotation, one orbit every 24 hours. From the ground, the satellite appears fixed in the sky. This is extraordinarily useful. A ground-based dish antenna can point at a single location and maintain a continuous link. Television providers use geostationary satellites to broadcast channels across entire continents. Weather agencies place satellites there to monitor hemispheres continuously, providing stable views for tracking storm development. Communications networks rely on the fixed position for reliable, always available connections. The downside is distance. Signals take about a quarter of a second to travel up and back, introducing noticeable delay in conversations. And because geostationary orbit sits above the equator, satellites can't see polar regions well. High northern or southern latitudes appear foreshortened and distant. But for mid-latitudes and tropics, geostationary orbit provides a stable platform, a ring of watchers circling the planet at the speed of its spin. Timekeeping extends beyond GPS. Satellites help distribute precise time to systems worldwide. Financial networks use synchronized timestamps to order transactions and prevent conflicts. Power grids coordinate the phase of alternating current across vast areas, ensuring that electricity flows smoothly. Telecommunications networks align data packets so transmissions don't collide. All of this depends on coordinated universal time, disseminated partly through satellites. Ground-based atomic clocks are more stable, but satellites make that precision available anywhere, anytime. A GPS receiver doesn't just give location, it gives time accurate to tens of nanoseconds. Data centers, stock exchanges, and cell towers pull timing signals from the sky, synchronizing their operations invisibly. If navigation satellites failed, maps would stop working. But so would many systems that depend on the timing signal as a hidden synchronization pulse. Earth-observing satellites go beyond weather. Some carry sensors tuned to specific wavelengths that reveal information invisible to the eye. Near-infrared light reflects strongly from healthy vegetation, allowing satellites to map forests, farmland and grasslands in detail, assessing crop health or tracking deforestation. Thermal infrared measures surface temperatures, urban heat islands, volcanic activity, ice sheet melt. Microwave radar penetrates clouds and darkness, mapping terrain and detecting subtle ground movements like subsidence or tectonic shifts. Ocean color sensors measure phytoplankton, concentrations tracking biological productivity and pollution. Satellites monitor ice thickness in polar regions, land use changes in cities and farms, air quality from fires and industry. These datasets feed into agriculture, forestry, disaster response, and climate science. Researchers use decades of satellite imagery to track changes over time, forests shrinking, glaciers retreating, cities expanding, building a long-term visual record of the planet's transformation. At the same time, other satellites look outward. Space telescopes observe the universe from above the atmosphere, avoiding distortion from turbulence and water vapor. Without air to scatter and absorb light, they record wavelengths that never reach the ground: far infrared, ultraviolet, X-rays. They sit in stable orbits or at special gravitational balance points, where the Sun and Earth's gravity combine to hold them in place relative to Earth. From there, they stare at distant galaxies, star-forming regions, exoplanets, black holes, building catalogues of cosmic phenomena. The sky becomes an observatory platform, offering a clear view outward that ground telescopes can't match. But ground telescopes still matter. Large observatories on mountaintops, above much of the atmosphere's water vapour, conduct wide-field surveys and follow-up observations. Recently, though, they've had to contend with satellite constellations. Long exposure images, meant to capture faint objects over minutes or hours, now sometimes include bright streaks where satellites pass through the frame. Astronomers and satellite operators are discussing mitigations: darker satellite surfaces, lower orbits that decay faster, adjustable schedules to avoid critical observations. Software tools are being developed to identify satellite trails and subtract them from images. The night sky is becoming a shared resource requiring coordination, balancing the need for global connectivity with the desire for dark, unobstructed views of the cosmos. The atmosphere itself is also managed. Air routes follow specific corridors and flight levels, coordinated by air traffic control. Planes don't fly randomly, they follow designated paths, separated by altitude and lateral spacing. GPS, radar and radio beacons help pilots navigate, while controllers on the ground coordinate takeoffs, landings and crossings. It's an invisible lattice in the lower sky, a three-dimensional highway system layered beneath the orbital paths above. Jets cruise at 10 to 12 kilometers, well below even the lowest satellites, but the principle is similar. Organized paths, constant monitoring, adjustments to avoid conflicts. Radio astronomy depends on quiet. Some observatories are built in radio quiet zones, areas where ground transmitters are restricted so faint cosmic signals aren't drowned out by terrestrial broadcasts. The Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, these facilities listen for radio waves from pulsars, distant galaxies, and the cosmic microwave background. As the sky fills with satellites and their radio links multiply, frequency management becomes critical. Astronomers coordinate with satellite operators, negotiating spectrum allocations and transmission schedules to protect certain frequencies for scientific observations. It's a shared challenge, balancing communication needs with the desire to listen for weak signals from the universe. Long-term climate monitoring comes from satellites that remain in orbit for decades, instruments recalibrated periodically to maintain consistency. They track sea level rise with radar altimeters, measure atmospheric carbon dioxide and methane, monitor ice sheet thickness with laser ranging, observe temperature changes across land and sea. These stable, multi-decade records allow scientists to distinguish short-term variability, El Niño years, volcanic eruptions, from long-term trends like warming temperatures and shifting precipitation patterns. Climate science depends heavily on this continuity, on instruments that watch the same things year after year, building datasets that reveal changes invisible in any single snapshot. Global navigation now blends multiple systems. Phones and vehicles combine GPS, GLONASS, Galileo, and Beidou signals, along with inertial sensors, compass readings, and map data. Ships use satellite navigation to cross oceans, planes to find runways in poor visibility, trucks to optimize routes, emergency services to locate callers. The system is so embedded that failures cause widespread disruption. Navigation systems offline mean delayed flights, lost ships, confused logistics. Some companies are adding low Earth orbit constellations to navigation systems, using faster-moving satellites to improve positioning accuracy and provide backup signals. The goal is resilience. If one system fails, others compensate, keeping the blue dot moving across the map. International bodies manage the sky's use. The International Telecommunication Union allocates radio spectrum and coordinates geostationary orbital slots to prevent interference. National space agencies license launches and satellite operations, requiring operators to follow debris mitigation guidelines, deorbiting satellites at end of life, avoiding certain crowded regions, reporting maneuvers. These are voluntary frameworks, not laws, but most operators comply because cooperation keeps the sky usable for everyone. As more countries and companies launch satellites, coordination becomes more complex. There are debates about who owns orbital space, whether certain orbits should be reserved, how to enforce rules when actors don't cooperate. The sky is becoming contested territory, requiring diplomacy alongside engineering. Light pollution affects views from both directions. Cities illuminate the night sky from below, washing out stars with scattered light from streetlights, billboards, and buildings. Dark sky advocates push for better lighting design, shielded fixtures, warmer colours, lower intensity, to reduce sky glow and preserve natural darkness. Now they also consider light from above, satellite reflections, bright surfaces catching sunlight and sending glints earthward. Some satellites have been redesigned with visors or darker coatings to reduce brightness, but thousands are already in orbit and more launch monthly. Stargazers find that the sky isn't just lit from cities anymore. It's also dotted with moving lights from machines overhead. Both sources diminish the view of stars, requiring new efforts to protect dark skies. Think of the sky as infrastructure, similar to roads and power grids but invisible. Satellites carry timing signals, data streams and observational records. Aircraft carry people and goods. Telescopes carry information inward from the cosmos. This overhead layer connects continents, instruments and archives. It's infrastructure you use daily without seeing. Your phone's location, the weather forecast, a video call across oceans, the synchronization of a power grid, the data flowing between servers. The sky supports a vast, quiet system that makes distant places feel near, makes information flow freely, makes global coordination possible. It's easy to forget because it's silent and far away, but it's there, always working, always looping, always linking. The rain continues outside, tapping steadily against the window. Drops merge and race down the glass in uneven paths, disappearing at the sill. The clouds hang heavy, blocking any view of stars or satellites. Somewhere above, invisible in daylight and weather, the machines continue their paths. GPS satellites broadcast timing signals. Weather satellites scan clouds and ocean temperatures. Communications satellites relay signals across continents. Telescopes in orbit photograph distant galaxies. Sensors measure Earth's forests and ice sheets. Debris drifts in slow orbits, tracked by ground stations. Aircraft follow their corridors below, passengers unaware of the navigation signals guiding them. The sky's not empty. It's full of movement and information, a layered network of purpose and precision. The rain falls, puddles form, and the world below goes about its routines. Above, the quiet machinery keeps turning, connecting maps and calls and forecasts, linking places too far apart to touch, making the planet feel smaller than it really is. You look up and see only clouds, but the sky is working. The next story is about to begin. Please relax and enjoy. The night sky holds no pictures. If you stripped away every human memory, every story whispered around fires, every child's pointing finger tracing invisible lines, you would be left with what actually exists. Scattered points of light at vastly different distances, burning with no awareness of each other, no knowledge of the shapes we claim to see. The constellations are not written in the cosmos. They are written in us, drawn by minds seeking pattern in randomness, order in chaos, a way to hold the infinite in something small enough to remember. Before cities glowed and screens flickered, the night was truly dark. When the sun dropped below the horizon, a different world emerged overhead. The Milky Way stretched like a river of milk across the black, so dense with stars that it seemed solid enough to walk upon. Against this backdrop, certain stars burned brighter, forming natural groupings that caught the eye. Early humans, sitting beneath this celestial theatre, began to connect the dots. They saw animals in the arrangements, hunters frozen mid-stride, boats sailing through darkness, tools they recognized from daily life. These patterns became more than decorative, they became functional. The shapes carried myths that taught moral lessons and preserved history. They marked the passage of time, signalling when to plant crops or when storms might come. For navigators crossing featureless oceans or endless deserts, the patterns became compasses, reliable friends that never slept. The stars themselves were patient teachers, returning night after night with clockwork precision. A person could spend a lifetime learning their rhythms, noting how certain patterns climbed higher each evening as weeks passed, how they shifted with the seasons in an endless cycle. Young children learned from elders which shapes to watch for, which stories belonged to which clusters of light. Knowledge passed down through generations became encoded in these celestial pictures, a form of memory storage more reliable than any oral tradition alone. The sky became a vast mnemonic device, where each pattern triggered recall of essential information: when to expect rains, which direction led to water, what time of year brought game animals through familiar paths. In this way, constellations functioned as humanity's first external hard drive, information stored not in the stars themselves, but in the relationship between stars and human minds trained to read them. Yet the remarkable thing about these pictures in the sky is that they were never universal. The same cluster of 7 bright stars that one culture called a bear was, to another, a wagon or a plough. Where Greeks saw a hunter with belt and sword, other societies recognized entirely different figures. The Chinese divided the heavens into their own palaces and courts, mapping celestial bureaucracies that mirrored earthly power structures. Egyptians placed their gods among the stars. Mesopotamians tracked planets through star patterns, recording their movements on clay tablets. Across the Pacific, Polynesian navigators learned intricate star paths, memorizing how different patterns rose and set at various latitudes, using this knowledge to cross thousands of miles of open ocean without instruments. Indigenous peoples of the Americas, Australia and Africa each developed rich astronomical traditions, their own constellations serving their own needs, telling their own stories. The sky became a palimpsest, the same star supporting layer upon layer of meaning, each culture inscribing its worldview on the shared canvas of night. Not every pattern carries the weight of official designation. There exists a distinction between constellations proper and what astronomers call asterisms. An asterism is an informal pattern, usually simple and memorable, often spanning multiple official constellation boundaries, or highlighting just a portion of one. The Big Dipper, perhaps the most famous pattern in northern skies, is actually an asterism within the larger constellation Ursa Major. The Southern Cross, crucial for navigation in the southern hemisphere, is similarly a recognisable asterism, though it has become so culturally significant that many treat it as a constellation in its own right. These simpler shapes serve as entry points, mnemonic devices that help stargazers find their way through more complex regions. They are the friendly landmarks in a sky that can otherwise seem overwhelmingly crowded with light. Meanwhile, true constellations function more like neighbourhoods or districts, regions with defined boundaries that cover every square degree of the celestial sphere. Within these regions might be multiple asterisms, stories, and deep sky wonders, but the constellation itself is simply an address, a way of organising space. Among all the star patterns, 12 hold special historical significance. These are the zodiac constellations, and their importance stems from geometry and accident. As Earth orbits the Sun appears to move against the background of distant stars, tracing a path across the sky over the course of a year. This apparent solar path is called the ecliptic, and it passes through a band of constellations that ancient observers noticed and named. The Moon and planets, whose orbits roughly align with Earth's orbital plane, also travel through this same band. Long before anyone understood that Earth was a planet orbiting the Sun, cultures recognized these patterns and their relationship to seasonal change. When the Sun occupied Aries, spring arrived. When it moved into Cancer, summer heat peaked. The zodiac became a calendar written in stars, a way to mark the Sun's seasonal position and anticipate agricultural cycles and religious festivals. These patterns acquired layers of meaning, becoming associated with personality traits, fortune-telling, and symbolic systems that persist today, even though most people never see the actual star patterns that gave them their names. But the relationship between these patterns and the seasons is not eternal. Earth spins on an axis tilted relative to its orbital plane, and this axis itself slowly wobbles like a spinning top winding down, completing one full wobble approximately every 26,000 years. This precession gradually shifts where Earth's axis points in space. Right now, the North Celestial Pole, the point in the sky directly above Earth's North Pole, lies near a star we call Polaris. Ancient Egyptians knew a different pole star. In 12,000 years, the pole will point near the bright star Vega instead. This wobble also shifts the apparent position of the Sun among the zodiac patterns over time. When astrology's traditional dates were established, the Sun entered Aries at the spring equinox. Now, due to precession, the Sun enters Pisces at that same moment. The stars haven't moved relative to each other. Earth's perspective has shifted. On human timescales, constellations appear fixed, permanent, but on the timescale of civilizations rising and falling, they drift, slowly rotating their relationship to seasons and cardinal directions. The stars themselves carry names, many of them ancient, handed down through centuries of observation. Bright stars often bear Arabic names, gifts from medieval Islamic scholars who preserved and advanced astronomical knowledge when much of Europe had forgotten it. Names like Betelgeuse, Rigel, Aldebaran and Altair come from Arabic descriptions of the stars' positions within their constellation figures. Other names stem from Greek or Latin traditions. Within each constellation, a system exists for cataloguing stars by brightness, using Greek letters, alpha for typically the brightest, beta for the second, gamma for the third, and so on down the alphabet. This system, called Bayer designation after the astronomer who popularized it, provides a rough hierarchy. But modern catalogues have assigned numerical designations to millions of stars, creating vast databases that cross-reference position, brightness, spectral type, and motion. The old names persist, though, because they carry poetry and history. Saying Betelgeuse evokes something that Alpha Orionis, or HD 39801, cannot. A connection to human observers across time who looked up and named what they saw. The modern constellation system, the one recognised by astronomers worldwide, solidified only in the 20th century. Before then, different star atlases showed slightly different constellation boundaries, overlapping patterns, and varying star assignments. In the 1920s, the International Astronomical Union, an organisation founded to bring order to astronomical nomenclature and standards, took on the task of formalising constellation boundaries. They settled on 88 official constellations, drawing precise borders using celestial coordinates. These borders follow lines of right ascension and declination, the celestial equivalent of longitude and latitude. Now every single point in the sky belongs to exactly one constellation, the way every spot on Earth falls within some nation's territory or the boundaries of an ocean. Some of these constellations bear ancient names with deep mythological roots. Others, particularly those in the southern sky or those filling gaps between older patterns, received modern, often uninspired names: Telescopium, Microscopium, Sextans, Circanus. The division wasn't based on story or cultural significance, but on practical need to cover the sphere completely, to give astronomers a standardized reference system. This system functions as a coordinate shorthand. While professional astronomers locate objects using precise right ascension and declination numbers, constellations provide useful context, especially for communication. Announcing a new supernova in Virgo immediately tells observers roughly where to point their telescopes, narrowing the search from the entire sky to a manageable region. Star charts, both historical and modern, divide the celestial sphere into these named sections, blending ancient storytelling with geometric precision. The constellation becomes both postal code and character, both map grid and myth. This dual nature, scientific and narrative simultaneously, makes constellations uniquely valuable teaching tools, bridges between the human need for story and the scientific need for systematic organisation. For much of human history, these patterns served intensely practical purposes. Long before GPS satellites and magnetic compasses, travellers and sailors found their way using stars. In the northern hemisphere, finding Polaris meant finding north, and Polaris could be located by following the pointer stars of the Big Dipper asterism. Once you knew which direction was north, other directions followed. In the southern hemisphere, where no bright star marks the celestial pole, navigators learned to use the Southern Cross and nearby pointer stars to approximate south. The altitude of certain stars above the horizon gave clues about latitude. Sailing toward the equator, northern constellations sank lower while southern patterns climbed higher. Experienced navigators memorized how patterns rose in the east, arced across the sky, and set in the west, using this celestial clockwork to judge time as well as direction. The patterns were more than pictures. They were instruments, tools embedded in memory rather than metal. The sky itself rotates through seasons, a slow carousel of patterns. Stand outside on a winter evening in the northern hemisphere, and you might see Orion dominating the southern sky, his belt unmistakable, accompanied by Taurus and Gemini. Return 6 months later in summer, and Orion has vanished, replaced by Scorpius low in the south, Sagittarius toward the thickest part of the Milky Way, Cygnus flying overhead. These seasonal appearances became calendars. When certain stars rose just before dawn, farmers knew planting time had arrived. When other patterns appeared at sunset, harvest approached. The cycle repeated with reassuring regularity, year after year, generation after generation. Cultures built their rhythms around these sky markers, timing migrations, festivals, and religious observances to stellar appearances. The sky was a book everyone could read, weather permitting, requiring no literacy or wealth, only clear nights and patient observation. Memory became encoded in pattern, knowledge preserved in stories attached to shapes. Each constellation typically carries not one story, but many, accumulated over centuries from different cultures and traditions. Take Orion, visible from almost everywhere on Earth. Greek tradition sees a hunter, boastful and bold, killed either by a scorpion or by the goddess Artemis, depending on which version you read, and placed in the sky opposite Scorpius, the two never appearing together, eternal enemies. But other cultures saw different figures in those same stars. Some saw a canoe, others a group of dancers, still others a farm tool or a deity's body. Chinese astronomy divided those stars among several of their own constellations, not recognizing a single unified figure. The multiplicity of stories demonstrates that constellations are narrative containers, flexible enough to hold whatever meaning a culture needs them to carry. They are not discoveries but inventions, collective creative acts repeated independently across the globe. The stars forming these patterns share nothing but our perspective. Within any given constellation, the stars typically lie at vastly different distances from Earth. Two stars that appear side by side in the sky might be separated by hundreds of light years, one relatively nearby, the other impossibly remote, appearing similar only because we view them along nearly the same line of sight. Their colours hint at their nature. Hot blue stars burn fiercely, cooler red stars smoulder, yellow stars like our sun occupy a middle ground. Brightness indicates not just intrinsic luminosity but also distance and size. A faint star might be dim because it's genuinely small and cool, or because it's extraordinarily far away, or both. Modern astronomy has measured these distances, revealing the three-dimensional structure hidden behind the two-dimensional pattern. The sky's depth, invisible to ancient observers, turns out to be vast beyond comprehension, with constellation patterns as flat projections of a deep reality. Even the patterns themselves are temporary, though on timescales so long they seemed eternal to those who first drew them. Stars move through space with their own individual velocities, called proper motion. The stars of the Big Dipper, for instance, are slowly drifting, and in 50,000 years the familiar shape will have warped into something unrecognizable. Ancient observers saw slightly different patterns than we do, though the changes during recorded human history are small, enough that ancient star maps remain largely recognizable. On geological or astronomical timescales, constellations dissolve and reform constantly. They are momentary alignments, meaningful only during the brief window of human civilization. Beings who might look up from Earth a million years from now would draw entirely different pictures, name entirely different patterns, the stars having reshuffled themselves across the sky. Between and within the constellation boundaries lie treasures beyond the stars themselves. Nebulae, vast clouds of gas and dust where new stars are born, glow with distinctive colours that reveal their chemical composition. Star clusters, groups of stars born together and still bound by gravity, appear as smudges to the naked eye, resolving into jewelled gatherings through telescopes. Galaxies, entire cities of billions of stars, hide within constellation borders, often requiring dark skies and optical aid to perceive it all. These deep sky objects often take the name of their host constellation for identification: the Orion Nebula, the Andromeda Galaxy, the Crab Nebula in Taurus. The constellation becomes an address, a way to direct attention to a specific region of the vast celestial sphere. Amateur astronomers learn the constellations as much for this practical navigation purpose as for the beauty of the patterns themselves. The southern sky posed a special challenge for European astronomers during the Age of Exploration. Mediterranean and northern European cultures had thoroughly mapped their visible sky, constellations stretching back to ancient Mesopotamia and beyond. But as ships sailed south, crossing the equator and reaching southern latitudes, new sky appeared, stars and patterns never seen from Europe. Early explorers and astronomers assigned new constellation names to these regions, often technical or contemporary rather than mythological: telescopium for the telescope, octans for the octant navigation instrument, microscopium for the microscope. Some southern constellations received exotic names: Tucana the toucan, Pavo the peacock, birds encountered in distant lands. Yet indigenous peoples of the southern hemisphere had always known this sky intimately, with their own rich traditions. Australian Aboriginal astronomy, for instance, recognised patterns in the dark lanes of the Milky Way itself, seeing an emu, a canoe, and other shapes formed not by bright stars but by the absence of light. by silhouetted dust clouds against the glowing band. These dark constellations represent another way of reading the sky, focusing on negative space and contrast, showing the variety of approaches human minds take when pattern seeking among the stars. The same sky that inspired scientific astronomy also gave rise to astrology, and the relationship between the two has always been complicated. Both use the same constellations, the same star names, the same positional measurements, but they diverge in purpose and method. Astronomy seeks to understand what celestial objects are, how they form, how they move, what they're made of, using observation and physical law to build predictive models of the universe. Astrology, with roots as old as astronomy itself, seeks meaning in celestial patterns, linking the positions of sun, moon, and planets among the zodiac constellations to human personality and fate. Modern science finds no mechanism for such influences and no evidence supporting astrological predictions, but the cultural hold of astrology remains strong, a testament to the human desire for cosmic significance. Constellations belong to both histories, factual and symbolic, scientific and mystical, evidence that the same patterns can mean radically different things depending on what questions you bring to them. Practical tools for learning the sky have evolved over centuries. Hand-drawn star charts, some dating back thousands of years, map constellation positions relative to horizon and zenith. Planispheres, circular tools with rotating disks, show which constellations are visible for any date and time, helping observers anticipate what they'll see before stepping outside. Modern smartphone apps use sensors to detect the phone's orientation, overlaying constellation shapes and labels on the camera view, transforming the phone into an interactive star map. Some apps simulate the sky from any location on Earth, any date in history or future, showing how the view changed or will change. These tools all share a common goal, making the overwhelming chaos of thousands of visible stars comprehensible by organizing them into named, memorable patterns. They translate the actual sky into something approachable, turning randomness into structure, teaching the eye what to look for. Yet many people today never see the sky these tools describe. Light pollution from cities washes out all but the brightest stars, reducing constellations to skeletal fragments. Where ancient observers saw the Milky Way as a river of light and could count hundreds of stars with naked eyes, modern urban dwellers might see only a dozen bright points on a clear night. The patterns become impossible to complete, the connections impossible to draw. This loss represents more than aesthetic deprivation. It severs a connection between humans and cosmos that existed for all of our history until the last century. Children who never see a star-filled sky miss something fundamental, some sense of scale and wonder and context for our place in the universe. Efforts to preserve dark skies, through regulations on outdoor lighting and establishment of dark sky reserves, aim to keep some places where the full glory of the night remains visible, where anyone can still step outside and see what our ancestors saw, the pictures they drew among points of scattered light. Constellations make excellent teaching tools because they meet learners where they are. A child or beginner can start by learning to recognize one obvious pattern: Orion's belt in winter, the Big Dipper in summer. From that anchor point they can learn to star hop, using known patterns to find adjacent ones, building outward gradually. Orion's belt points down towards Sirius, the brightest star in the night sky, part of Canis Major. The Big Dipper's handle extends in an arc toward Arcturus, a bright orange star in Boötes. These connections transform a bewildering sky into a navigable space, each new pattern linked to the previous one through memory and recognition. As familiarity grows, deeper lessons emerge naturally: why stars have different colours, what makes some bright and others faint, how distance and intrinsic luminosity combine to create apparent brightness. The planets, wandering through the zodiac constellations, reveal the solar system's flatness. Nebulae and galaxies demonstrate that stars are merely the most obvious inhabitants of space. Constellations become the framework supporting more sophisticated understanding, the skeleton onto which flesh and detail can be added. If humans ever establish colonies on Mars or venture to planets around other stars, the constellations will change or vanish. From Mars, the view differs only slightly. Earth is close enough that most patterns remain recognizable, though some stars shift position by a degree or two. But from a planet orbiting Alpha Centauri, our nearest stellar neighbour, the entire sky would look alien. Stars that appear bright from Earth might be faint or invisible from there, while others currently dim would blaze prominently. The constellations we know would mean nothing. Colonists would undoubtedly draw their own patterns, name their own figures, create their own mythology from a different arrangement of lights. This thought experiment emphasizes how local and temporary our constellations are tied specifically to Earth's vantage point and to the brief moment of human civilization. They are not universal truths, but cultural artifacts, meaningful precisely because they are ours, shared heritage of everyone who has ever looked up from this particular world. Despite the enormous diversity of constellation traditions, something remarkable emerges: convergence. Many cultures, independently, noticed the same bright groupings and recognized them as significant, even when they assigned different names and stories. The 7 bright stars of the Big Dipper, or Ursa Major, appear in countless cultural traditions, sometimes as an animal, sometimes as a vehicle, sometimes as figures or objects, but almost always recognized as a distinct unit. The Pleiades, a tight cluster visible as a small glowing patch to the naked eye, appears in myths from every inhabited continent, called the Seven Sisters in some traditions, different names elsewhere, but always noted, always significant. This overlap suggests that certain patterns are particularly compelling to human perception, bright enough and distinctly grouped enough that they naturally catch attention. The sky becomes a shared heritage, an informal global collaboration where different cultures independently marked the same celestial landmarks, even as they interpreted them through different lenses. We all looked up at the same stars and felt compelled to organize them, to name them, to tell stories about them. That universal impulse connects us across time and culture. End with the rain still falling softly, a gentle percussion above in the darkness. Somewhere beyond the clouds and the rain, the stars continue shining, indifferent to weather, to human observation, to the names and stories and patterns we impose upon them. The stars are not in Orion. They are simply there, burning through nuclear fusion, each one a sun in its own right, some dying, some being born, all following the laws of physics through 3-dimensional space that our flat perspective flattens into pictures. The constellations exist only in the slender region where starlight meets human mind, where scattered points become connected shapes, where randomness becomes pattern because pattern helps us remember, helps us navigate, helps us tell our stories. They are soft pencil lines drawn on a page of lights, invisible tracery connecting dot to dot, imagination's geometry projected onto reality. Under the quiet hush of falling rain, you can imagine that sky above the clouds, the ancient patterns waiting there unchanged, the same stars that guided sailors and marked seasons for farmers, the same lights that inspired myths and poetry and wonder. The pictures aren't real, but the act of drawing them, that collective creative gesture reaching across millennia, that might be the most real thing about us. Creatures who look at chaos and insist on finding meaning, who see points of light and draw lines between them, who stand beneath the infinite and make it memorable, make it ours, make it home. And perhaps that is enough, that simple human act of pointing upward and saying, "There, see that pattern, let me tell you its story," passing knowledge from one generation to the next through pictures that exist nowhere except in the space between our eyes and the stars, in the fertile ground of imagination where all meaning grows. The rain continues its quiet work, washing the world below while the universe spins on above, patient and vast, waiting for the clouds to part, for someone to look up again and trace those ancient lines, to remember that we are creatures who need our stories written large across the night, need to feel that the heavens themselves participate in our narratives, that the universe, however indifferent it may be, at least provides the canvas on which we paint our brief and brilliant meanings. The next story is about to begin. Please relax and enjoy.